Ah, okay. We were muted. Okay. So, uh, and we have at our division several laboratories, laboratory of dosimetry and environmental radioactivity. I'm head of this laboratory, laboratory of heterogeneous processes of radionuclides and labeled compounds, laboratory of nuclear chemical methods of analysis together with Ms. Bauer laboratory. They are working on, let's say, material science using the Ms. Bauer spectroscopy techniques. Quite new laboratories, laboratory of radiopharmaceutical chemistry and laboratory of chemical physics of F elements. And the newest one, laboratory that is a bit on the side. It is interdivisional laboratory of smart chemical design, and tomorrow it will be a lecture from the head of this laboratory. They are working on using of quantum chemical calculations and machine learning to investigate the properties of the materials, molecules, etc., etc. And all these laboratories, I would say that we have very strong collaboration between every laboratory. We have a lot of common topics and we work together. That's why I can say that radiochemistry division is like a big family. So it's not really strong competition between laboratories, but a strong collaboration. And the strong sides of our division, it is, of course, that we can work with radioactive materials. We have these hot labs to work with quite a large amounts of radioactive substances, but also we have quite a lot of analytical techniques, including radioanalytical techniques. We have transmission electron microscopy, photoelectron spectroscopy, and we also in this laboratory of chemical physics of F elements, we have a rather new spectrometer of the X-ray absorption spectroscopy for X-ray absorption spectroscopy. We have also an agreement with IAA on educational and training programs. So recently, in previous years, there were quite a lot of also schools on different aspects of radiochemistry, on waste management, together with IAA. And today, during our schools, international schools on radiochemistry, we have experts from IAA. So this collaboration is still ongoing, and it's really good. And we have also, for example, one of the master students, he is already working in IAA, currently working, and our alumnus, they are also some of them working in International Atomic Energy Agency. As I already mentioned, we have this state license. It is very important for us because if we would not have this license to work with radioactive substances, we were not able to make our research work at all because we are specialized in radiochemistry. Here's the list. It's not a full list, not a complete list of the radionuclides that we are allowed to work with. And so if you are interested in working with some certain radionuclides, we can look in our license to search if there is a radionuclide in the list of our license, but it's not a complete list. And as I mentioned, we have this rather new technique, this laboratory scaled X-ray absorption spectrometer that we can use to investigate substances, to analyze substances in both solid states and crystal structure, their crystal structure, or it can be amorphous materials like glasses or others. It can be materials liquid materials, like organic or aqueous solutions. And yeah, so in theory, it can be even gaseous materials. But we didn't work with the gaseous substances yet, but liquid and different solid materials we can work with. So we can investigate the oxidation state of the certain element. We can analyze the local structure, local surrounding of this element, and it can work even during the chemical process. One of the project here was to investigate the oxidation state of the cobalt during the in the batteries during charge and discharge of the batteries. So without opening the battery, we can see what is happening inside with the certain elements. And today we have 3 master program in the field of the decommissioning of nuclear facilities, in spent nuclear fuel management, and in radiopharmaceutical chemistry. As I mentioned, we have a list of already held international schools on radiochemistry, summer schools and winter schools, and today it is number 9 of these international schools on radiochemistry, and I hope it is quite interesting and successful. So there is a list of different topics that were covered already during these schools, and it is an open list. So at the end of the school, you will get a list of questions. We will ask your feedback, and if you are interested in some of the topics for the future international schools on radiochemistry, you can write down what will be good in your opinion to hear for the next summer or winter school. Yeah, and going back to our division, what we are doing here, it is different research topics. I just listed main topics, but it is not, again, the complete list, and we are always looking for a new topic. So the main topics are radiology and environmental radioactivity, and today it is becoming even more and more important. Of course, the peak of interest was after the Chernobyl accident, then during the and after the Fukushima accident in radiology. But today, due to the decommissioning of the many of nuclear facilities, it is becoming very important to investigate the contaminated areas around the nuclear facilities and to analyze what is happening with radionuclides in these conditions in environment, and how to treat, how to manage these huge contaminated territories safely and, of course, efficiently, both from the chemical point of view and from economical point of view. And nowadays there are more and more research works and yeah, applied works in these topics due to the decommissioning of the different facilities. Of course, it is geological disposal of radioactive waste, because in Russia nowadays it is the huge projects on the construction of the final disposal or final repository of the high-level waste. It will be the first such disposal for solid high-level waste in Russia. And it will be in Krasnoyarsk region, so the project is already ongoing. The first stage of this project is finished. It is the construction of the building, of the facilities on the surface, so administrative buildings, electricity supply, and other such buildings. They are already constructed, and they started already boring the wells to construct the underground research laboratory, so it is in the next stage, and then the underground research laboratory will be constructed. There will be a very long period of time to investigate this certain site or place, if it is suitable for final repository of high-level waste. We hope that yes, otherwise it will take much more time to choose another place and again start all this work from the beginning. So we hope that everything will be fine. And yeah, the next stage after the 235, it will be the construction of the repository itself. Due to the decommissioning, there is a need for the remediation of the territory, and also nowadays we used the same techniques that we used for sorption and purification of the radioactive waste. We use the same techniques to remediate the territories that are contaminated not with radiochemical or radioactive substances, but with just, let's say, normal chemical substances like maybe oil or some products from the chemical industry. And so we developed these different sorption systems to remediate these territories as well, to remove, for example, heavy metals as one of the example. As I mentioned, we have a laboratory of radiopharmaceutical chemistry, and we are working now a lot on different aspects of nuclear medicine, starting with the radionuclide production. So it is the irradiation of the targets, irradiation in using accelerators or using nuclear reactors. And then my colleagues, and they develop the schemes how to extract very efficiently and selectively the radionuclide that will further used in the nuclear medicine, because there are a lot of requirements for the radionuclide that are used in medicine. They have to be very pure from the chemical point of view, from the radiochemical point of view, and all these reactions, when we label the organic compounds, they have to be very efficient without a lot of byproducts. So it is very complex topics, but very important, because nuclear medicine, especially diagnostics, I believe is the most powerful techniques for diagnosis of the not only for cancer diseases, but also for other brain diseases, and not only this, cardio diseases and many others. To help both this isotope or radionuclide production, remediation techniques, or purification of radioactive waste, we are investigating the separation chemistry. And separation chemistry, again, it is here I would like to stress attention that we investigate the fundamental aspects of the extraction or sorption of the radionuclides on different materials. And with this information about the fundamental peculiarities of this process, we can propose which system will help in a certain task for separation of the specific radionuclides. And our colleagues in Ms. Bauer laboratory and in the laboratory of physical chemistry of F elements, they're working a lot on material science, and it includes magnetic materials, batteries, and also radioactive materials as well. It can be, again, liquid systems for investigation, the separation chemistry, for example, or it can be materials from the nuclear fuel cycle that we will go through later, and many others. As I mentioned, we have a new laboratory that are dealing with the quantum chemical calculations. I should add here also, and machine learning techniques for investigation of the properties of the materials, of the properties of the new compounds, organic compounds and inorganic compounds, and also, as you will hear tomorrow, how to find the materials with the desired properties. So we are starting not from the composition of the material, but we are starting from the desired properties, and we have tried to find the composition of the material with these properties. And the last but not the least, we're working at our division with the labeled organic matter to use these labeled molecules and huge molecules like proteins, for example, to investigate different biochemical processes. And just I will go just shortly through these examples. Radiopharmaceutical, as I mentioned, we are starting with the very complex, they're not very complex, but very long way, I would say, to use different general approaches for separation, like liquid-liquid extraction, sorption on different sorbents. And we combine these different approaches, these different sorbents, to develop the best system for separation of pure radionuclide, desired radionuclide. And with this radionuclide, there is a very long way to investigate the characteristics of the complexes of our radionuclide with the organic molecules that will be further used in the medicine, in the pharmaceutical. So it is investigation of the labeling conditions of these organic molecules. Then it is studies in vitro, so it's just biological environments and maybe biological cells. And then it is in vivo, so we use mice. We have vivarium in our division, so we can use mice to investigate the distribution of the radiopharmaceutical inside the body of the mice. So it's preclinical, let's say, investigations. Extraction studies or separation studies that are used for choosing the best system for separation of different radionuclides. One of the example, it is use of these extractants in the processing of the spent nuclear fuel. And again, during this school, we will go through different processes like Purex process, Urex process, and other processes to see different approaches in different countries, how they treat the spent nuclear fuel. And one of the most complex tasks was to separate very close, chemically close elements like americium and curium and lanthanides. They're all trivalent, they all have identical chemical properties. And after several years of research, we found the best molecule with a good separation factor. And in coming years, maybe in to 2026, we will use one of this molecule in pilot industrial scale to separate the americium and curium. Another interesting example of the use of this spectroscopic technique is the investigation of the mechanisms of extraction. And it was really surprising for us that even for the element which chemistry is known very well, especially in aqueous solution, uranium. So uranium is known more than 200 years, and of course after the second half of the 20th century, the chemistry of uranium was investigated very intensively. And even for this element during its extraction, we found a new mechanism of extraction when uranium extracted in this complex simultaneously in cationic and anionic form. So even for the very well-known element, we can find something new and interesting. With the help of our colleagues from the Laboratory of Smart Chemical Design who are working on quantum chemistry and machine learning, we built a model to predict the radiation stability of the organic molecules. It is at the moment not quantitative, not fully quantitative model, but semi-quantitative, so we can at least compare different molecules between each other. And if we know from experimental data the stability of one or two molecules, then we can build the full range of, so full prediction of the stability of other molecules. And you will also see how important different barriers during the storage and disposal of the both spent nuclear fuel and high-level waste, because in different countries there are different strategies for the nuclear fuel cycle, open or closed nuclear fuel cycle. In one of them there is a disposal of spent nuclear fuel, and another it is disposal of high-level waste, but still the approaches to make the storages and disposals, repositories safe, the approaches are the same: to build a system of the engineered and natural barriers to make the storage and repository safe. And there are different requirements for these engineered barriers, and we are in our laboratories investigating the properties of these barrier materials. It may be clay materials, it can be cementitious materials, depending on their density, composition, etc., etc. So there is a homemade diffusion cells that are used to investigate their properties. And with the information on the properties of the sorbents or these engineered barriers that we obtain in laboratory conditions, so we investigate in the well-controlled conditions, for example, the sorption behavior of the radionuclides on our material. From this data, from this experimental data, we obtain the values for the thermodynamic constant of the chemical reactions during the sorption. For example, sorption, it can be also extraction as well, but here's sorption. And we can use it further to model the behavior of the radionuclide in different conditions, with the changing of pH or ionic strength or the composition of the groundwater, for example. Also, we are working quite a lot on the including studies on nuclear forensics. It is investigation of the nuclear materials as well as radioactive materials, investigating the properties starting from the nanoscale, let's say, size. It is the colloids that were extracted from the groundwaters near the Mayak plant reprocessing spent nuclear fuel. So it is really a small colloidal particles, so it's 10 microns, and it was found that, for example, plutonium and uranium, they are bound mainly to iron and manganese colloids, and they are not traveling as a soluble ionic species. For example, they are traveling, they are transported in the groundwaters as solid particles because they are sorbed on these particles. So it is from nano and micro scale to the macro scale. So it is it is photo of the elephant foot from the Chernobyl reactor. So not reactor, but already under the reactor, these rooms. And this sample of this elephant foot that was collected by our colleagues from the St. Petersburg Institute, Radium Institute, we investigated this particle that was collected already around 30 years ago. During the storage of this particle and epoxy resin, you can see this radiation damage of this epoxy resin. And it was interesting for us to see, I don't know if you can see these layers, how the melted substance, so it is like waves, let's say. And this melted substance, it was step by step solidified. So it was a really interesting investigation on the composition, on the morphology of these materials. And again, going back to the laboratory conditions, we are investigating the solubility behavior of the different materials. In this example, it is different dioxides, starting with cerium dioxide as a model for plutonium dioxide, and then thorium dioxide, uranium dioxide, and finally plutonium dioxide, to see if there are any peculiarities in their behavior. Can we really use cerium dioxide, for example, as analog for plutonium? In many applications, yes, but not in all, of course, applications. And the work that is related to the high-level waste repository that I mentioned in the beginning in Krasnoyarsk region, we are working on investigation the properties of the rock samples that are extracted from this site in Krasnoyarsk region, and we see how different radionuclides interacts with different minerals in of this rock. And with this investigation, we are calculating the specific constant for the sorption of the radionuclides on different minerals. So if we have information, the full information of the composition of the minerals in the site, we can propose the model for the migration of the radionuclides through the fractures. So together with the laboratory investigation, with the field studies, so analysis of the environmental samples, we can build a good model for the behavior of the radionuclide. So analyzing the real samples, we can fit our models to the real systems. Maybe some parameters can be fitted, and this information can be further used for the modeling of the migration of the radionuclides from the repository during the very long period of time, up to 100,000 years or longer. Also, as I mentioned, as far as there are a lot of different decommissioning of the nuclear facilities, there is an interest in the analyzing of the natural samples around these facilities. And it is not only the soil, for example, and maybe plants, but also my colleagues are working with the not animals, with the fishes, with the living organisms, fishes, bacteria, and other organisms in these objects. And finally, yeah, one of the tasks of this analysis is to develop a new methods, new techniques for the rapid analysis of the environmental samples. I think, yeah, it is all for this lecture. So, and now we will listen you later, yeah, at the end of this day before our icebreaker, before our joint dinner. But before, there is another job for you. It is a small testing, as usual. And again, please write your name and family name. We will not use it in when we will count the different scores. We will not use your family name in the presentations. It just so family name and names. It just for recording that all of you are here and you perform these testings. But for evaluation of this test, we will not use your name. So don't be afraid of this. So also every day, probably due to the end of the year, some of the colleagues they have changes in their schedules. So we will have changes also in our schedule, and every morning we will have this information about the schedule for this day. Okay, and one of the most important information, the washrooms are located on the second and the first floor. So on the right side from the stair, the first door is for men, and the second door is for women. And now testing. Mosh. So, уже? Уже отвечено. Зараз.
So this list to the side on a daily basis, so always be here.
Okay. So let's start with the lectures, and the first lecture will be, I would say, already classical one. It's just the basics of nuclear fuel cycle, because everything that we will, not everything, but some of the lectures from, for example, Andrei Yuri Shadrin, they will be based on the basics information of nuclear fuel cycle. So just for a reminder, we will go through different steps. And again, as a reminder that today still the situation after a few years is also not changing very much. Still, there are quite a huge energy poverty in different countries, in African countries, especially in Latin America, in some Asian country. And it is important not only from the point of view of the industry, but also the lack of the energy leads to the, oh, sorry, there's something, yeah, sorry. The lack of the energy leads to the bad health care, because for the health care, you just one, okay, the sound is on. You need electricity supply, because all the medical equipment requires electricity, and if you have no energy, you will have no good medical care. So that's why, due to the information from the World Health Organization today, around 1 billion people has no sufficient health care due to the energy poverty. And of course, one of the biggest challenge is to reduce the use of the fossil fuels, because it is not only the emission of the greenhouse gases, but also a lot of different organic pollutants that can cause different diseases. And it is, for me, it was very good example in China, because nowadays a lot of cars in China, at least in the big cities, they are electric wheels. I've been in Beijing first time in 2013, and now 10 years later, it is really a big difference when people started to use electric vehicles. Of course, we can say that they were forced to use it, but forced with the let's say soft power, because with the electric wheels you have less taxes, you have some preferentials, you can park easily, and also as I know, for example, in Shenzhen, in Guangdong province, there is a limit for the registration of the normal cars, yeah, with the normal engines. There is some certain number, I don't remember how many cars they can register per year. So if there is no available limits, you cannot even register your car. And there is no limits for electric wheels. So again, it is like forcing people to use electric cars, and it's really make a big difference on air characteristic air conditions. And to decrease the use of the fossil fuels and to reach the climate goals that the humankind would like to reach, so at least to keep the temperature at the level that we have today, it was forecast by the International Atomic Energy Agency that by 2050 we need to have around 80% of all electricity supplies to be low carbon. So in low carbon, it's of course not only nuclear energy, it is wind energy, solar energy, hydropower energy. But you can see that it is really a big challenge. Today it is only 30%, and to reach 80%, it is a huge challenge. And it is not only related to the climate change and pollution of the air. We can see again from the statistics, all the sources are listed here, that these four kind of energies, nuclear, hydro, wind, and solar energies, they're also the safest sources of energy. So here counted death rates from the accidents and air pollution. And accidents means all the accidents starting from the mining of the ores and the production of the electricity. And we can hear every year that in this or other country there is accident in coal mines, and I don't know, 20, 30 people died due to this accident. And it is a lot of such accident all over the world. And that's why coal mining, for example, is one of the most dangerous source of the energy. And fortunately, likely we don't hear such events on mining of uranium or accidents at nuclear power plants. Yeah, if you ask people outside on the streets how many nuclear accidents they know, maybe they will say 2 or maybe 3 accidents, and that's it. Of course, there were much more accidents than that we know about Chernobyl, Fukushima, maybe 3 Mile Island, or Windscale fire, or Kishtim accidents, or whatever. But there were more, but with not such a huge impact on the human deaths or injuries. So and we can say that nuclear energy is really one of the safest. Of course, any news about the accidents or some events with the radioactive materials, they produce a lot of noise, a lot of rumors in the news, and people really like to see something happened with the radioactive materials. A few years ago, it was a story in Moscow when the new road was constructed on the east part of the Moscow, and it was necessary to build one of the construction part near the old facility. There they produce the rare earths. So it was the plant for processing of the ores for the production of the rare earths. And it was known for the scientific society and for industrial society that outside of this facility there is a storage of the radioactive waste that are produced during the processing of these ores. They contain mainly thorium and the decay products, natural thorium, yeah, and products of the decay of the thorium. And it was a program, a very long-term program to remove this storage with these natural radioactive materials. Every year, 1 or 2 trucks excavated this waste and transported to the Sergeyev Posad, where special company Radon is located. They are responsible for all radioactive waste in Moscow and around Moscow region. So it was a very long program, long-term program. And when people started to construct this road, the new road, it was really a big discussion in news, in TV, that that there is a storage of radioactive waste in Moscow. What a disaster! It was like a new information, but of course everybody knew about this. About the storages, and yeah, that means that I would just point out that any information that is related to the radioactive substances are very sensitive in public. But actually, if we will look in statistics, again, nuclear energy source is one of the safest source of energy. And of course, it is one of the cleanest source in terms of the greenhouse gas emissions. Here, all the greenhouse gas emissions are counted, including the building construction of the nuclear power plants, because during the construction of the nuclear power plants, we use the cementitious materials and cements. The production of cements is one of the source of the CO2 in the atmosphere as well. And also during the mining, many trucks, they using the kerosene. So again, the production of the CO2. So it's not absolute zero, yeah, but some very low number if we compare it with other sources of the energy. So again, nuclear energy and these 3 other types of energy, they are really the cleanest and the safest sources of energy. And nuclear energy also is very concentrated source of energy. Energy of nuclear bonding, nuclear reactions, they're 100,000 times more stronger than any chemical bonds. Yeah? So that means that the energy that is produced, I don't know, I hope people can hear me online. That means that the energy that is produced from the same volume of the fuel, if we take gas or oil, it will be million times less in comparison with the nuclear fuel. So just a comparison, 26 cubic meters of gas is equal to just 26 milliliters of the nuclear fuel. The energy will be the same. And also that leads to the surface or area that is needed for the operation of the nuclear power plants or for the operation of the wind or solar power plants. Even if, again, these 2 types of energy, they're also cleanest and safest. Nothing is safe absolutely. Yeah, so they are one of the cleanest and safest. Still, the advantage of the nuclear power plant is the use of smaller area for the same production, for the production of the same amount of energy. And together, all these 4 types of energy, they are forming or considered to form so-called green square, where nuclear power plants and hydropower sources, they produce constant electricity supply because they independent on the weather conditions, on the climate conditions, and so they can produce constantly the same at the same level energy. But for the very intensive use of energy, then, for example, during the daylight, when all the people come into the working place, there is a peak in the energy consumption. So for this additional consumption of energy, the wind powers and the solar powers can be used as additional sources, for example. And so nuclear energy, also nuclear power plants, the advantage of nuclear power plants that the typical period of operation of nuclear power plants is more than 50 years. So if you build a nuclear power plant, that means that more than 50 years you will have a stable source of energy. And also the main cost in the production of electricity with nuclear power plants is the cost of construction of nuclear power plants. It's very costly because there are a lot of systems for safety systems, and that's why nuclear power plants are very expensive. But the fuel itself is only 5 to 10% of the cost of the electricity produced. So that means that if you, during the years, if the price for the uranium will increase even twice, that means that the cost of the electricity production, if we will not count, of course, the salary increase, prices, etc. So the increase due to the increase of the cost of the price of the fuel will increase also only 5 to 10%. So it is very sustainable source of energy. So the price is not really dependent on the price of the fuel itself, and it is not the same for the fossil fuels like oil and gas. And so nuclear power plants can provide the long-term security for the supply of electricity, and it is a really sustainable source of energy. But for us, as for scientists and for people who operate maybe nuclear power plants or facilities for radioactive waste or spent nuclear fuel management and treatment, for us, it is important to build the trust of the public that we can handle with these nuclear power plants and also radioactive waste that are arised in a safe way. Yeah. So that is our goal in life, one of the goal in life. And this year, it is a really iconic year, I would say, because it is a 70th anniversary of the operation of the first industrial nuclear power plant. Of course, there were other nuclear reactors before this year, but these nuclear reactors, they were either research reactors or they were industrial reactors in terms of the production of plutonium for military projects. And the first non-military nuclear reactor that were connected to the electric grid in the city was a reactor in Obninsk. So it was constructed for the one aim to produce electricity. So it is the first real industrial nuclear power plant. And it was started, its operation started in June 1954, and the full capacity energy production was reached in October, if I remember correctly, in 1954. So it is 70 years of the operation of the first nuclear power plant. And today we are already talking about the generation 4 of the nuclear reactors that are much more safe, much more efficient in energy production. This first reactor, you can see that it was very small, and the energy, the power of this reactor was just 5 megawatts. So today it's too low. It's even not a research reactor. Yeah, and today we're talking about the reactors of 1,000, 1,200 megawatt, and maybe even more. But it was important step at that time. And then people talking about the nuclear energy, very often they imagine the nuclear power plant and that's it. But we know that nuclear power plant is just one step in a nuclear fuel cycle. And nuclear fuel cycle includes all operations starting from the uranium ore mining, then extraction of uranium, purification of uranium, conversion uranium to uranium hexafluoride, then enrichment of uranium with the isotope uranium-235, then fabrication of fuel, so it's a back conversion of uranium hexafluoride to uranium dioxide, then fabrication of the nuclear fuel, and only at this stage we put fuel assemblies in nuclear reactor. And it's not a final step, of course. After working in nuclear reactor, there is further story of the spent nuclear fuel. First of all, it is stored for several years in cooling ponds in nuclear power plants, and then there are two ways, two strategies to handle the spent nuclear fuel. Either it is a direct disposal of the spent nuclear fuel underground to the 400, 500 meters in geological disposal, like in Sweden, in Finland, in proposal in the USA and in some other countries, or it is a reprocessing of the spent nuclear fuel with the extraction of the fissile components like uranium and plutonium, and with some other components we will see later, and production of the fresh fuel, either uranium fuel or MOX fuel, mixed oxide fuel, and use these fissile materials again. So, and that is that we call the closed nuclear fuel cycle. Of course, during the closed nuclear fuel cycle, there is a production of the high-level waste, but their volume is much, much smaller than the volume of the spent nuclear fuel, and and we cannot use these materials anymore. So let's go just through the steps of the nuclear fuel cycle, step by step. We are starting with the mining of uranium ore. There are three main types of the mining. Either it is carriers, it is mines, or it is underground leaching. It depends on the conditions, how uranium is present in this specific place. If there is minerals with, let's say, with concentrated uranium, like iron minerals of the uranium that we can follow, that we can extract just one mineral and follow this mineral formation, then it is more convenient to use mines. You don't need to extract the full volume of the rocks. Yeah, just this small amount of this specific mineral. Unfortunately, there are not such a lot of mines with such conditions. Very often, uranium is dispersed in the rocks, in ores. That's why there is a need to take all these ores out on the daylight surface to form hills of this ore, and there is a dripping of the sulfuric acid, for example. So all the uranium particles are dissolving, and there is a collection of this solution containing uranium, and further purification either with extraction or with sorption or with other techniques. And underground leaching, of course. What's the underground leaching? There are several wells. One well is for injection of the leaching solution. Again, leaching solution, mainly it is solutions of the sulfuric acid, and one central well, it is a recovery well where you take out this leaching solution. So when leaching solution go through these ores, through these rocks, there is a dissolution of uranium minerals, and you collect this solution enriched with the uranium salts, and then you send this solution to the facility where you extract uranium. But for underground leaching, there is a need for certain conditions. Your ore, your containing uranium, should be permeable for leaching solution, and also there should be rocks that prevent the transport of the solution through these layers. Yeah, it may be clay formations, for example, that are not permeable for aqueous solutions. So there is a need for certain geological conditions, and again, it is not always possible. But underground leaching is one of the cleanest methods for extraction of uranium, because there is only wells that are located in the field, and so it looks like these pipelines and wells, and when there is very depleted ore already, so no uranium is leached anymore. You just remove all these pipelines, seal the wells, and that's it. So your field is remediated in 10-15 years naturally. For leaching, as I mentioned, very often the sulfuric acid solution are used, but sometimes if the uranium ore is located in carbonate rocks, it is not possible to use sulfuric acid because you will produce a lot of gases, and it is bad for the technological process. In this case, there is a use of sodium carbonate solution. In this case, uranium also form very soluble carbonate complexes, and they are dissolved in aqueous solution, and you extract uranium. So depending again on the geological condition, you can use either acidic conditions or alkaline conditions for leaching of uranium. After the extraction and purification, first purification of uranium, there is a set of operations to again to purify, to make uranium very pure from a chemical point of view, because for uranium, for nuclear fuel, there is a very strict requirements for the impurities in uranium. So there is additional purification stages, and the final product of these purification stages is so-called ammonium diuranate. It is a formal structure, actually, as we see from the publications, there are no such a compound as ammonium diuranate. It's just formula to write approximate stoichiometry of this substance, let's say. But yeah, for practical use, people very often use this name, ammonium diuranate or ADU process. And this ammonium diuranate used further to produce uranium dioxide that can be transported for the next facility. The uranium dioxide transformed to uranium tetrafluoride and then to uranium hexafluoride. And uranium hexafluoride is a unique compound. It has a very low sublimation temperature, around 56 Celsius degrees, and that means that it can be transformed to the gaseous state at very low 56 at very low temperature, and can be used further for the enrichment. Yeah, and also why it is a unique compound, because fortunately for us, for humans, natural fluorine has only one isotope, stable isotope. That means that there is not a very wide variety of masses. For example, if it would be oxygen, it would be 6 more different masses. And with only one isotope of fluorine, there are only 2 masses, uranium-235 plus 6 fluorines, and uranium-238 plus 6 fluorines. In natural uranium, it is approximately 0.7% of uranium-235, and for most of the nuclear reactors that are used today, the enrichment, the fraction of uranium-235 in the fuel should be from 2 to 5%. So we need to enrich our natural uranium with the isotope uranium-235 up to these values. Higher values, they're used for some specific nuclear reactors. It is either transport nuclear reactors in icebreakers or in submarines, or it is use of in the research reactors, so it's some specific types of the nuclear reactors. But for energy productions, for most of the types of the reactors, this enrichment 2 to 5% is enough. And to perform this enrichment, 2 main types of the techniques are used. It is either a gas diffusion method, where you have a metallic membrane with the pore size of from 10 to 100 nanometers, and under high pressure you push the gas containing both isotopes through this membrane, and according to isotopic effect, uranium-235 is moving a bit faster through this membrane, and thus you obtain the flux with the higher concentration of uranium-235. There's not a complete separation of 2 isotopes. It's just step-by-step enrichment with the uranium-235 isotope. Another technique that is used nowadays in Russia, it is use of the gas centrifuges. In this case, there is a formation of the, let's say, high gravitational forces in the centrifuge, and according to the just normal physical laws, the higher the mass, the faster it goes to the bottom. But in this case, bottom is just the wall of the centrifuge, so it's not a vertical field, it's a horizontal field of the forces. So the bottom is just a wall of the centrifuge, and the light fraction is collected in the middle of the centrifuge. So you separate two fluxes containing light fraction and heavy fraction. Of course, again, it is not a complete separation at one stage. You need hundreds, and sometimes, depending on the degree of the enrichment, you need thousands of this centrifuge. So the facility, one of the facility looks like this. It is a Siberian chemical plant where you see this huge, very long buildings around 1 kilometer long, where it is filled with these centrifuges. So, yeah, the production is costly. And the main fuel, nuclear fuel today, that is used in nuclear reactors, it is uranium dioxide. And today we can say that also uranium, the mixed oxide fuel, plutonium and uranium dioxide fuel, is used in nuclear reactors. Last year it was also another iconic milestone, because in the reactor BN 800 in Russia, in Sverdlovsk region, Ekaterinburg region, the active core of the reactor was completely filled with the MOX fuel. So it was originally designed to work with the MOX fuel, but at that time when BN 800 was started, its operation started, there was no facility to produce such a lot of MOX fuel. So after a few years in Krasnoyarsk region, the plant for production of the MOX fuel was constructed and operated. So the capacity of this production of the MOX fuel is enough to completely fill the active core of the BN 800 reactor. So it was the first time, at least in Russia, when the industrial nuclear reactor was completely filled with the MOX fuel. For research reactors and for new types of the reactors, there are another types of fuel. One of the most important of them is nitride fuel, because it is the fuel that is supposed to work for new fast neutron reactors with the lead as a coolant. But there are some experimental reactors, for example, for transportation of the minor actinides. It is the molten salt reactor, and there will be a lecture next week about this reactor. But you can see there are plenty of other varieties of the fuel, for example, composite fuel, triso fuel, and other composite fuels. They are supposed to work for high temperature gas reactors. And yeah, I took it from Wikipedia, sorry for that. It's just a general scheme of the nuclear power plant. I think it shows very nicely the general scheme. We have an active core of the reactor. We have a coolant that is circulating here, and the coolant, depending on the type of the reactor, can be either water or gas or liquid metal or molten salt, depending on the design of the reactor. Then there is a steam generator, so the heat from this coolant is transferred to the steam generator, so it's just water and production of the steam, and steam rotating the generator, and the electricity is produced. So it's just a general scheme. And of course, there are plenty of the details for each type of the, not only nuclear reactor, but the nuclear power plant itself. If we will look on the main types of the reactors that are used for the production or are planned to be used in the production of the electricity, I would say more than 80% of all the reactors, they are pressurized light water reactors, so either VVRs or PVRs. It is boiling water reactors. It is some very few pressurized heavy water reactors. It is still working uranium graphite reactors that we call RBMK, or sometimes you can see that they are called Chernobyl type reactors, but yeah, they're still in operation after a lot of modifications. And new reactors, fast neutron reactors, they are not completely new. Yeah, for example, sodium-cooled reactors, they are under operation more than 30 years already in Russia, and they're still working. And but there is a plan for the advanced gas-cooled reactors or high-temperature gas reactors. And yeah, about the fast neutron reactors, it is not only sodium cooled reactors like BN types, but also another liquid metals like lead, or its mixture with bismuth. And why we need uranium-235 in the nuclear fuel? Here it is a diagram of the neutron cross-section for the fission of uranium and plutonium. So that means, in simple words, it is a probability of the nuclear reactions, specifically fission nuclear reaction, yeah, because there can be different nuclear reactions. For example, just catching or capture of the neutron without the fission of the uranium. And here it is specifically for the fission of the uranium and plutonium. And you can see that for the thermal nuclear reactors, that means for the neutrons with very low energy, and why they're called thermal, because the energy of the neutrons are close to the thermal movement of the atoms at this temperature. Yeah, that's why they're thermal. You can see that the probability or cross-section of these reactions are very high for uranium-235 and plutonium-239. But in nature, we don't have a lot, at least, at least a lot of plutonium-239. Of course, we have some plutonium-39 due to the accidents and explosions, etc., but not enough to dig it, to mine it, and produce nuclear fuel. So we have uranium, natural uranium. That's why we need uranium-235. That we take from nature, and you can see that the probability of this fission reaction is very high. But from the spent nuclear fuel, we can extract plutonium that is also very good in terms of the fission, so in terms of to be the fuel for the nuclear reactors. But for the high energy neutrons that we call fast neutrons, you can see that at this region, the probability of the fission for uranium-235, for plutonium-239, and for uranium-238, these probabilities become very close. That means that in fast neutron reactors, we can use not only enriched uranium, but also the depleted uranium-238. And it is a very good chance for us to use all the uranium that we already excavated, that we already produced, in the fast neutron reactors and produce more and more energy. And it is not the only reason to develop the fast neutron reactors. So if we will look on again which type of fuels we are using today, it is mainly uranium dioxide for thermal neutron reactors, and it is enriched uranium dioxide. It is MOX fuel that can be used both for thermal, because you can see that cross section for plutonium is high enough, so we can use this MOX fuel both for thermal and the fast neutron reactors. And for fast neutron reactors, today the new fuel is already developed, and there is already a construction completed for the production of the mixed nitride uranium plutonium fuel. Why we need nitride? Because in this case nitride has higher density, so that means you have a higher concentration of the fissile materials in the reactor. And as far as we are using uranium-238, and you can see that the cross sections are lower for fast neutrons than for thermal neutrons, that means that you need more higher concentration of the fissile materials in the core. That's why another type of fuel, more dense fuel, are used for fast neutron reactors. And as I mentioned, BN 800, so it's not last, it's already 2 years ago, was completely filled with the MOX fuel. And when nuclear fuel is working in the reactor, there are plenty of new elements are formed. So just imagine that we are putting in the reactor only 2 elements, uranium and oxygen. And after working, you can see that around 50 more elements are producing inside the nuclear fuel. There is a distribution of the yield of the fission products. You can see that it's not just half and half. It's like 1.5 ratio between the masses of the most probable fission products that are produced due to the fission. And also, I would like to mention that the scale is logarithmic scale. So the yield of these components and these components, the difference 100 times and even more. But still, even if the yield is not very high, there are a lot of new elements. So you can see that the most probable masses of the fission products are around 90 and 140. That's why 2 radionuclides are very important when we are talking about the radioactive or nuclear waste. It is cesium-137 and strontium-90, because they are the main components of the fission products in the spent nuclear fuel. And the nature of these fission products are very different. The half of the periodic table are inside the spent nuclear fuel now, and they form they are gaseous products, so that's why they are forming such a porous structure of the grains of the spent nuclear fuel. So if you will see such a porous structure of the uranium dioxide, you can immediately say that it is a spent nuclear fuel, or at least this material was inside the nuclear reactors, because it is a trace or notation that the gaseous products were produced, and mainly due to the nuclear fission. So it's gaseous products. It is metals. This where are they? These epsilon phase metals. Epsilon particles. It is metallic particles inside the oxide fuel. Yeah, so absolutely different materials. There is a formation of very soluble components that can form their own oxides, or they can be combined with the other, let's say, non-metallic components like chloride, iodide, etc. So you produce not only different elements inside the spent nuclear fuel, but different compounds inside the nuclear fuel. That's why, due to these changes of the composition of the phase composition, there is changes not only in structure, but that is more important in the physical properties, mainly thermal conductivity of the fuel. The temperature in the central part of the tablet of the nuclear pellet is up to 1000 Celsius degrees, maybe even more. And the temperature of the coolant outside of this pellet is about 300 Celsius degrees. So it's a huge gradient of the temperatures. Yeah. And if your material has low thermal conductivity, that means that there is no possibility for the temperature to be transferred from the center to the wall, and that means that the temperature in the middle will increase. Yeah, and it will be a very severe accident with the melting of the fuel of the core, and it is a very, very bad situation, the worst situation in the nuclear reactor. So that's why within the time when the properties of the nuclear fuel is changing, after some time, there is a need to replace the spent nuclear fuel with the fresh fuel. And it doesn't mean that we don't have fissile materials anymore. Yeah, it just properties of the material is not good anymore, and we have to replace it. Because actually there is only 3% of the mass of the material that we cannot use any longer. Yeah. Where? Rim, yes, rim. It's just a circle, let's say. The plutonium is migrated to the boundary, outer boundary of the pellet, and form so-called rim or ring. You can circle of the plutonium enriched phase. Yeah. Yeah, and there is only 3% of the mass of the initial material that we cannot use longer. Yeah, and this 3% of the mass make the spent nuclear fuel to be not possible to be used in the nuclear reactor. But you can see that there are plenty of uranium, also uranium-238 and uranium-235 that we can use. And also, due to the neutron capture reaction, not neutron fission, but neutron capture reactions, there is a production of plutonium and some other actinides. And plutonium, as we already saw, can be used also as a part of the fresh nuclear fuel. That's why it is one of the strategy to extract all these materials that can be used again, and left only 3% of the initial mass as a high-level waste. Yeah, it's a good strategy. And just a reminder, what is the waste, what we call radioactive waste. First of all, of course, it is material that contains some radioactive substances, yeah, some radionuclides. And also, there is no further use with current technologies. Yeah, maybe in future there will be some another technologies that can use this material, but currently we cannot use it anymore. And there is another important part of this definition, that the concentration of these radionuclides should exceed the clearance levels that are established by the government or authorities in individual countries. Yeah, in different countries, these levels can be different. International Atomic Energy Agency provide some recommendations on how to classify radioactive waste, what levels can be, but each country decided by its own, what levels will be in their law, in its law. And in the closed nuclear fuel cycle, just a reminder again that spent nuclear fuel is not a radioactive waste, even from the point of view of the law. Yeah, and there is a different laws to manage radioactive waste and the spent nuclear fuel. Yeah, again, that in open nuclear fuel cycle, there is a direct disposal of spent nuclear fuel without reprocessing, and in a closed nuclear fuel cycle, spent nuclear fuel is the source of the fissile materials and not a waste. Okay. And today in Russia and in other countries, in France, in China, in India, if I remember correctly, there is a strategy for so-called dual component nuclear energy. So what does it mean? We have a light water reactors, so it is a thermal neutron reactors. We have uranium dioxide fuel from the natural uranium, let's say, and we produce a spent nuclear fuel, but in thermal nuclear reactors, there is a production of the plutonium with not very good isotopic composition. It's not only plutonium-239, there are also plutonium-40 and other even isotopes of the plutonium that are not very good for thermal nuclear reactors. So this fuel goes to the reprocessing plant, and plutonium, this let's say bad plutonium, goes to the fabrication of the MOX fuel, and this MOX fuel with bad plutonium goes to the fast neutron reactors, where due to the neutron physics and nuclear reactions, there I'm not expert at the moment, there is some number of the nuclear reactions where plutonium, due to the again presence of uranium, there is a changes of the isotopic composition of plutonium with the let's say enrichment of the plutonium with the good isotopes of plutonium, plutonium-239 specifically, and this good plutonium, high fissile plutonium, goes again to the reprocessing plant, where the MOX fuel with the good plutonium goes to the thermal neutron reactors. So you can see these cycles where the end of the back-end stages of the thermal neutron reactors, they become the initial stages of the fuel production for the fast neutron reactors, yeah, and vice versa. Here, the good plutonium become a fuel for the thermal nuclear reactors, and these cycles they can be repeated several times. Nobody knows at the moment how many times, because such experimental investigations they are not currently finished. So it is a question now for the physicist, the reactor physicist, how many times these operations can be repeated. But we can see and we can say today that it is not only twice, it is more than maybe 5 times at least, maybe even more. So there is no need in natural uranium, no big need in natural uranium, because we again have a lot of the depleted uranium that are used in the production of the MOX fuel. And you can see that the plutonium that is produced is involved in this cycle completely. So there is a good source of the fissile materials in this dual, not infinite, of course, but very a lot of many times recycled fuel. And of course, there is a need in the development of new technologies to work with new types of fuel, to produce new types of fuel in terms of the isotopic composition of the fuel. There is need to develop the radiochemical technologies for separation of the deep separation of the components of the spent nuclear fuel from uranium and plutonium. And there is another benefit for spent nuclear fuel reprocessing. Yeah, there is a representation of the radiotoxicity of the material, and this is a spent nuclear fuel after extraction from the reactor. And you can see that this material keeps its danger or hazard for a very long period of time, more than 200,000 years. And here it is comparison with the natural uranium ore. So this equivalent to the natural uranium ore is reached after 200,000 years, so very long period of time. That means that if we put the spent nuclear fuel underground without reprocessing, we have to prove that our repository will be safe for this very, very long period of time. For me, it is I can understand this safety assessments of the repository, that it is very stable rock formations, etc., etc. A lot of engineer barriers to prevent the migration of the radionuclides. But still, if we imagine that the whole history of the humankind as a Homo sapiens is around 100,000 years. Yeah, that means that since very long time, when people even didn't have, I don't know, writing skills, and till the moment it's only 100,000 years, and we have to prove that our repository will be safe for even longer time. So it's very tricky, I would say. But if we remove the long-lived radionuclides, plutonium, that we involve in the nuclear fuel cycle, if we remove, there is no notation, but if we remove neptunium and americium with very long half-lives, then the rest will be only fission products like cesium, strontium, maybe some others. And already after 300 years, they will reach, in terms of radiotoxicity, the equivalent of natural uranium ore. And 300 years is already visible for us. For example, St. Petersburg was built, was founded 300 years ago. Moscow State University will be 270 years in January. So it's the period of time that we can see, and we can see a lot of buildings and constructions that are still safe. So we have techniques that will provide the safety at least for this period of time. So that means that the benefit of the spent nuclear fuel reprocessing is not only the full involvement of the fissile materials in the cycle, but also to decrease by 1,000 times the time when these materials will be dangerous or hazardous. Yeah. So it's a very good goal for me. And but yeah, the question that if we remove long-lived radionuclides from these materials, it doesn't mean that we avoid them. Yeah, so we just put them from one place to another. Yeah, they still exist. And to make them not exist, we use transmutation. And for this, we will need to use the fast neutron reactors. Either it is BN types of reactors or new type of the reactor with the lead as a coolant of the active core, or molten salt reactors, and it will be another lecture on molten salt reactor. In all of these cases, there is a high cross section or high probability for neutrons to convert long-lived radionuclides either in a shorter-lived radionuclides or to make fission products with, for example, with neptunium and with some part of americium. So in any type of these nuclear reactions, we convert the long-lived radionuclides with very long half-life to the shorter-lived radionuclides. And also with the involvement of the long-lived actinides in this cycle, we reduce the volume of the high-level waste. So here is the representation. I don't remember from whom I took this picture in one of the conference in India. I just make a picture of the slide and use it now. Sorry. So it was a representation of the volume of high-level waste with the techniques that we use today with the Purex process, for example, where we extract only uranium and plutonium, and all the rest of the actinides, americium, curium, are stayed in high-level waste. And it is the volume of the full volume of the waste that will be generated if we provide electricity by nuclear energy for one family. So it's 4 members in a lifetime. So it is 75 years of living. So, and it is only this small cube or cylinder of the waste. Every day we produce much larger amount of the plastic waste, for example, yeah, or other waste. And it is for people in 75 years. It's not a huge volume, but if we remove all the long-lived radionuclides, the volume will be even smaller. It's just one diamond in this ring. So it's very, very tiny amount of the high-level radioactive waste that will possess hazard only within 300 years. So it's a very good strategy that at least it seems like a good strategy. There are a lot of problems, of course, and we will talk about these problems, because how to separate all these radionuclides. Today, the main techniques that we use to separate all these 50 more elements in spent nuclear fuel, it is a liquid extraction. Yeah, when we dissolve spent nuclear fuel in nitric acid solution, then we extract uranium, plutonium, and some other elements in organic phase by tributyl phosphate, and then the rest, the raffinates, the aqueous solution is very high active aqueous solution, and so we produce a lot of liquids that are contaminated with radionuclides, and the idea of this new strategy is to avoid the formation of the liquid radioactive waste. That means that it is also a circulation of the streams in the reprocessing plant when we recover nitric acid and use it again, recover all the water that is evaporated during operations and use it again. So to reduce the volume of the radioactive waste, liquid radioactive waste, and to avoid the formation of the liquid radioactive waste that go from the reprocessing plant. There is so it is forbidden to produce liquid radioactive waste outside of the reprocessing plant. And it is a representation of the Purex process. We will have a lecture on Wednesday on the history of Purex process and some other aspects of the reprocessing of spent nuclear fuel. It's just a short maybe reminder or new information for you. So again, after the dissolution of the spent nuclear fuel in nitric acid, we separate mainly uranium and plutonium, but not only them. Actually, it is also technetium, neptunium goes there, and some other maybe components. And but mainly we extract uranium and plutonium with TBP in kerosene. And then we use reducing washing, so reducing agents to reduce plutonium to plutonium-free. And plutonium in trivalent state is not extractable, so it goes to the aqueous phase. And uranium stays in organic phase. So in this way, we separate uranium and plutonium. So first, we separate uranium and plutonium together. So we purify them from all these fission product, most of the fission products, and then we separate plutonium and uranium because the production of the MOX fuel requires at the moment separated uranium and plutonium. But for the separation of all other components of the spent nuclear fuel, a lot of new molecules of new systems are under development. And it will be another lecture on Thursday about the different schemes for the fractionation of the high-level waste. And today in Russia, we have only one working or operating spent nuclear fuel reprocessing plant that is called Production Association Mayak. The capacity, the designed capacity for this facility is 400 tons of spent nuclear fuel per year. And it started operation, I think, around 50 years ago. So it's quite old. And the benefit, the huge advantage of this reprocessing plant, that it can reprocess any type of fuel. It can work with the VVR fuel, RBMK fuel, this transport reactor, spent nuclear fuel, and any type of fuel. And today there is already constructed and should be in operation next year reprocessing pilot demonstration center at a mining chemical combine in Krasnoyarsk region facility. So it's again demonstrating center. The idea was that there will be a demonstration of the new technologies for the reprocessing of spent nuclear fuel, and the design of this facility is the capacity is 220 tons of spent nuclear fuel per year. And yeah, next year it should start not next year, in 2026 should start the operation of the spent nuclear fuel reprocessing. And there's another facility, small facility, but very important for us. It is called Experimental Demonstration Energy Center in Siberian Chemical Combine. It is in Tomsk region, city of Seversk. So the idea of this experimental energy center is to demonstrate that there is a possibility to perform the full closed nuclear fuel cycle on one site. So there is a new type of the reactor, this Brest 300. So it's also pilot reactor 300. It is a power of this reactor 300 megawatt. So it's really a small reactor, but with the coolant as lead, with this nitrite fuel, mixed nitrite fuel, and it will be around 10 tons of spent nuclear fuel every year taken from the reactor. So the capacity of this facility is designed for this 10 tons of spent nuclear fuel, of this reactor. So it will be a reactor. It will be a reprocessing of spent nuclear fuel facility. It will be a facility, it is already constructed, a facility of fabrication or production of the fresh nuclear fuel, and a facility for the immobilization of the radioactive waste. So the full closed nuclear fuel cycle on one site. And the idea is to demonstrate the possibility of such cycle and to calculate the economical parameters of all these operations. And this idea will be scaled up as an industrial energy complex with, of course, much larger reactors. It will be reactors with the 1,200 megawatt production, 2 reactors with this closed nuclear fuel cycle on one side. So it will be industrial energy complex. And we see now that, for example, in China, the idea is the same, but with the another amount of the reactors. They are thinking about of 6 or 8 reactors on one side with this closed nuclear fuel cycle. So we will see how it will work. And currently, this site is under construction. So the fabrication facility, nuclear fuel fabrication facility is already constructed. Reactor is under construction, and it should be finished in 5 years, if I correct. And next year, it will be a start of the construction of the reprocessing of the spent nuclear fuel facility. So it is a really ongoing project. It will be very interesting to see how it will work. Yeah, the problem of all this reprocessing operations is the formation of liquid waste. And in the past, it was not very big attitude to this liquid waste. The idea, the main goal was to create a nuclear weapon, and nobody really thought about the ecological issues. That's why many of this liquid radioactive waste, they were disposed in the lakes and the rivers, and it resulted in the contamination of huge territories. But nowadays, as I mentioned, there is a restriction of the putting of the liquid radioactive waste in open aqueous streams. And just a few words about the barrier systems for high-level waste that will be produced anyway during the reprocessing of spent nuclear fuel, or it is the same barrier system for the spent nuclear fuels, yeah, like in Finland and Sweden, that they are creating now. And there are 2 types of barriers. It is engineered barrier system that is consist of the matrix of radioactive waste. It is canister of the radioactive waste. It is the overpack of this canister, and the material between the rock and between the overpack. It is mainly the clay materials that have very low water permeability and very high sorption properties towards the radionuclide. So it's engineered barrier system and natural barrier system. So it's rock materials itself. So it's around 4 to 500 meters of the host rock. Yeah, and the good point of the radioactive waste that they are decaying. Yeah, so their danger is finite. So after several years, there is no more danger, let's say, above the natural levels of these materials. That is not the case for the materials like mercury, for example, that is stable. Yeah, and waste containing mercury will be dangerous forever. And radioactive waste, they have a finite danger or hazard. So, and yeah, just a brief conclusions that the nuclear energy today is an important source of clean and safe energy, of course, not in absolute terms, but in comparative terms. And nuclear fuel cycle, it is not only a nuclear power plant, yeah, it's all the steps from the beginning, from the mining of uranium ore to the disposal of the spent nuclear fuel or high-level radioactive waste. And radioactive waste, they are formed everywhere when we work with the radioactive materials. So, but the hazard is finite. So that is all from my side for today. If you have any questions, yeah, please. But just a moment. We have a mic. So that's people online can hear us.
All right. So my question is about the liquid radioactive waste. Is there any like processes that it can undergo to reduce maybe the volume, so we don't have like much liquid waste after?
Yeah, of course, to reduce the volume of the radioactive waste, one of the first steps for liquid radioactive waste is the evaporation. Either evaporation or filtration or some osmosis, so to reduce the volume of the liquid radioactive waste. Yeah, and depends on the specific activity of the of these liquids. It can be a very high degree of evaporation, up to the salts, yeah, down to the salts. So if the activity is low enough that these salts will be like intermediate level of waste or even low level waste. But if the solution initially is very active, it is no way to reduce the activity because the solution will boil by itself. Yeah, so by the heat production of the radionuclide. In this case, this liquid waste, they are immobilized in glass mainly. Yeah, today it is the only matrix to immobilize the high-level waste. And these liquids, they are before calcination, they are evaporated, but not to reduce volume for storage, but just to reduce the volume of water that goes to the furnace. Yeah, so they goes to the furnace with the components of the glass, and they are melted there. Water goes out, and the glass is formed. So first, of course, melted material, then it goes to the canister and cool down to form the glass. Yeah, so liquid waste, of course, if it is possible, they are concentrated before the further treatment. Yeah.
Thank you very much. Related to the complex, as you say, we consider some integrating the fuel fabrication. And I want to know what is the idea behind of this approach, because as you know, it's not economy.
Yes,
For
yes.
example, we very a small part for fuel fabrication,
Mhm.
fuel production, fuel separation, specifically in the reprocessing. If, as you know, we need optimal throughput for the have optimization, economy optimization. But I don't know if you explain it. It's my thank you.
Yeah. The problem for big country is transportation. So if you have only one, of course, if you have very big plant, from economical point of view, it is more efficient. But if you have this only one central plant, that means that you need to transport all the spent nuclear fuels, and in Russia, for example, it's very huge distances. Yeah, it's 8,000 kilometers, and you need to transport very dangerous materials with all these safety issues, with the military persons guarded these trains and all these problems. And it is also very costly. And if you have the full integrated system near the nuclear power plant, there is no need for transportation. So you reduce this cost. So, of course, as I mentioned, the idea of this experimental energy center to calculate all these economical parameters for such system, because it is not really obvious what the cost will be of all this operation. And also, as I mentioned, the only one reprocessing plant can handle any type of spent nuclear fuel. But if you have only one type of fuel, you can optimize all the processes. So that's now the purpose of this demonstration center, to see how it will work from economic point of view. And that's why, as you mentioned, that the larger the plant, the more economically efficient it will be. That's why in China, they're thinking of not 2 nuclear power plants, but about 6 or 8 nuclear power plants, because then you will have a larger facility. Yeah. Mm-hmm. Okay, any more questions? If not, if everybody is already hungry. So we finish with this lecture, and we will meet at 2 p.m. with my colleagues, who will tell you about the nuclear fuel production, about nuclear reactors. Okay, thank you. Yes.
So, dear colleagues, I think we should start. I guess other participants will join us in 1 minute, maybe less. Okay, and next lecture will be from Mikhail Volgin, who is currently working in Institute of Physical Chemistry and Electrochemistry of Russian Academy of Science. So, Mikhail, please.
Good afternoon, everyone. And the topic of my today's lecture is nuclear reactors and types of nuclear fuel. We'll start from very basic principles of energy generation, and the main energy production force is sustained and controlled fission chain reaction. It produces heat, which is then transferred to coolant. Coolant is vaporizing, the steam is generated, and this steam generates energy itself. One of the key characteristics of the chain fission reaction is breeding coefficient, or Kf. The formula for which you can see in the slide, it's the number of neutrons produced in the current generation to the number of neutrons absorbed and leaked in the present generation. If this coefficient is equal to 1, then we have a critical condition and the reaction does not stop, but it doesn't produce much more and more energy with every generation. If we have this coefficient more than 1, then we have a supercritical condition, and then the explosion can occur, or if we control this coefficient very, very precise, we can raise the power of the reactor. And so if this coefficient is less than 1, the power of the reactor is decreasing. So for the reactor, you need fissile material. For the fission reaction, you need sometimes moderator if you are working on heat neutrons. And of course, you have to have coolant to transfer your heat from the reactor core to the turbine. So mainly reactors are classified classified based on what coolant they use, on what moderator they used, and on what neutron spectrum they use. If we talk about neutron spectrum, we can divide reactors into 2 main groups: thermal reactors. I'm sorry, I have pointed the wrong energy. They should be exchanged with places. For thermal reactors, the neutron energy is about half of electron volt, and for fast reactors, the neutron energy is more than 100 kilo electron volts. So if we're speaking about thermal reactors, we can classify them due to the moderators they use. It can be either light water, it's normal water, or heavy water, water enriched with deuterium, or it can be graphite. And if we are speaking about coolant, we can divide reactors by we can divide reactors on reactors that use light water as coolant, heavy water as coolant, gas-cooled reactors, and liquid metal-cooled reactors. The first three groups of coolants can be used in thermal reactors, while no water can be used in fast reactors, because water is also a moderator, and in fast reactors we don't want our neutrons to be moderated and to reach a thermal level of energy. Also, there are a lot of classification based on the design of the reactor, and you can really invent many ways to classify them. So on the left, in the left part of the slide, you can see quite a lot of types of nuclear reactors that have been invented by humanity. No, I have said that sadly these energies should be exchanged by their places. This is the wrong position. For thermal reactors, neutron energy should be null pet, 1.5 electron volts, and for fast reactors, the energy should be more than 100 kilo electron volts. So in the left part of the slide, you can see maybe not all, but the most parts of the most types of the reactors that have been invented. But there are about only 6 types that are commonly used. They are pressurized water reactor, boiling water reactor, pressurized heavy water reactor, light water cooled graphite moderated reactor, gas cooled reactor, and the liquid metal fast breeder reactor. And we'll shortly discuss each of these 6 types. First, we'll start with pressurized water reactor. It's the most common reactor worldwide. There have been made about 277 units, and not made, it's operated about 277 units, and also 49 units of pressurized heavy water reactors, but technically they are quite the same. The main feature of this reactor is that it have 2 coolant loops that transfer energy from the reactor core. The first loop is radioactive and it is under high pressure. You can see the pressure is about 150 atmospheres, and the temperature is around 320 degrees centigrade. And due to the high pressure, even at this high temperature, the water stays in liquid state. So we don't have any steam in the first loop of the pressurized water reactor. The next modification is boiling water reactor. Technically, it has 1 loop of coolants that transfer energy from the reactor core. The water in this loop is radioactive, and also as far as it has to push the turbine, there is a vapor fraction in the outlet of the reactor core. The pressure is lower, about 70 atmospheres, and the temperature is about 290 degrees centigrade. This type of reactor is quite common in Western countries, and there are about 80 units in operation by 2016. Then we can name light water cooled graphite moderated reactor. Technically, it is close to boiling water reactor, but the moderation of neutrons is made not by the water, but by graphite. So you have graphite brickwork with channels, and some channels are for fuel, some channels are for control rods, and some channels are for tubes with coolant that take away the heat from this graphite brickwork. This type of reactor technically originated from reactors made to produce weapon plutonium, and they have, due to this, some advantages in maintenance. For example, the fuel assemblies can be exchanged without shutting the reactor down, which is very convenient, especially for producing plutonium. And also it can work on low uranium enrichment of about 2.5%. This type of reactors is mostly present in countries of the former Soviet Union, and by 2016 there were 15 units in operation. Then we can name gas-cooled reactor. It is mainly a British feature. The neutrons are also moderated by graphite brickwork, but the coolant of the first loop is not the water, it is gaseous CO2. It has high temperature, so it has higher thermal efficiency. It means that more heat is converted into electricity than in a normal water cooled reactor. But the disadvantage of this type of reactor is that low burn-ups of fuel can be achieved, and the fuel is not used efficiently there. And there are 15 units, and as far as I understand, they are mainly situated in Britain. And the last but not the least type of the reactor is a liquid metal fast breeder reactor. It's not a new one type of the reactor. It was invented in 1960s, but like humanity thinks that it's a promising type of reactor to burn down minor actinides and to use depleted uranium to produce more plutonium. The main features of these types of reactor, of liquid cooled reactors, are the absence of moderator, because we're working with neutrons of fast spectrum. It has higher power density, and the core itself can be smaller. And it has the potential to produce fissile material such as plutonium 239 from uranium 238, and it has potential to burn down long-lived minor actinides. So it is very promising for sustainable and closed nuclear fuel cycle. But for nowadays, there are only 2 units in operation, and both of them are in Russia. They are BN 600 and BN 800. Also, I should mention about fashionable word generation. Many people like to classificate everything by generations, and nuclear reactors are not the exception. 4 generations are named. The first generation is the first generation of reactors that are the reactors that were introduced the first in the 1950s. They have low electricity powers and are quite unsafe and unstable. The second generation is represented by nearly the most working reactors in the world. They have powers of about from 800 to 1,500 megawatts. And they are commercially available, or at least were. And the third generation is technically quite the same as the second generation, but it has improvements in the safety issues. like safer fuels, safer materials, and safer control interfaces, which will be spoken about a little bit later. And the fourth generation is the generation of the future, from which people want the 60-year working life, high economical efficiency, high safety, high fuel efficiency, and the facility in decommissioning and waste management. To say the truth, even the reactors of the second generation are working for 60 years sometimes, but every time they have this, their lifespan has to be prolongated with additional experiments. While the fourth generation reactors should have the 60 years lifespan in like their basic configuration from the beginning. And surprisingly, 6 types of the fourth gen reactors are named. It is sodium fast reactor, lead fast reactor. Technically, they are metal cooled breeding fast reactors. Very high temperature reactor where the coolant is gaseous. Gas fast reactor, and so a supercritical water reactor, and molten salt reactor. So we'll speak about nuclear fuel, an essential part of nuclear reactor without which it can't work at all. So fuels can be classified mainly by 2 features, by designs and by fuel metrics. So we'll start with classification by fuel metrics. The most common and the most widely used type of matrix is oxide, or to say precisely, dioxide of uranium, or mixed oxide of uranium and plutonium. It has many advantages, such as high melting temperature, radiation damage stability. It is quite chemical inert, so it can be stored even in the air without losing its properties, and also its interaction with cladding materials is quite low. And also it is not very excellent, but it is good in retention of fission products, both solid and gaseous. But there are also disadvantages in this fuel material, and one of the main disadvantages is low thermal conductivity. Due to this, in fuel pellet, very big temperature gradient occurs. So on the edge of the pellet, you can have temperature of about 500, 600 degrees centigrade, while in the central line of the pellet, you will have temperatures aiming towards the mark of 2000 degrees centigrade. And it is this temperatures stand apart from each other only on several of millimeters. And this leads to recrystallization of fuel, resintering, and various types of defects, which also decreases its hardness and can sometimes lead to fracture of the pellet. And also the other disadvantage is the low density of fissile atoms, so you cannot create a small and compact nuclear core. Also, there are several modifications of oxide fuels. One of the most popular modifications is MOX fuel. It's about 80% of uranium dioxide mixed with 20% of plutonium dioxide, and it is the fuel designated for use in liquid metal fast breeding reactors. Also, Rosatom produce remix fuel. It's technically a MOX fuel, but it has lesser part of plutonium dioxide mix, only about 4 to 5%, and it's designated for use in pressurized water reactors. Also, different oxides of rare earth elements can be mixed for different purposes. Sometimes chromium oxides can be mixed to improve fabrication and stability of the fuel. So it's a working horse of contemporary nuclear energy industry. The second fuel matrix is metal. The pure uranium metal is not used as a fuel matrix due to several issues. The first issue is its chemical activity. The uranium powder burns in the air, and it oxidizes very fast in the air. So usually alloys are used. The most common alloys are alloys with zirconium and molybdenum. It's about 10% of zirconium and 10% of molybdenum. Anyway, the production of these alloys is still complicated because you still need to deal with metallic uranium, and it's not very easy, but the obtained alloys are quite stable and do not oxidize, at least fast, at the air. But why should we use metallic fuels? Mainly for two purposes. The first purpose is that it has high thermal conductivity, so you won't have such a thermal gradient as in oxide fuels, and it's beneficial to the engineers when they are designing the core, because they it's a little bit easier for them to count it properly. And the second beneficial thing is high density of fissile atoms, which enables us to make reactors with high power density. And it's essential if we are speaking about transport reactors or research reactors, where we want to minimize the volume of the reactor and core itself. But even without manufacturing problems, there are problems with fuel cladding interactions, because mostly cladding is made from metals, and metals tend to react with metals more likely than metals with ceramic. And also metal fuel has problems with retaining gaseous products, and big swelling is not normal, but is a part of metal fuel. And the last and not widely used but promising fuel is nitrate fuel, or it is, to say precise, mononitrate of uranium, or mixed mononitrate of uranium and plutonium. It is also known as dense fuel. It has some advantages of the metallic fuel while retaining some advantages of the ceramic fuel. The advantage of the metallic fuel is high fissile atoms density and high thermal conductivity, while the advantage of ceramic fuel is the high melting temperature of about 1,800 degrees centigrade. But there are problems with this fuel, and mainly they are connected to the manufacture of uranium nitride. It is very complex and not complex, complicated, and it will be told to you in the second lecture. Also, the nitride fuel can oxidize quite rapidly in the air, and in some cases even burn as uranium metal, which is not advantageous at all. And also, if we use a normal nitrogen that is present in the air, and it's mostly the 14 nitrogen, we'll get a lot of radioactive waste in the form of 14 carbon. So the usage of 15 nitrogen is obligatory if we don't want to manage a huge amount of gaseous radioactive waste. But still, due to its physical appearance and physical characteristics, it's a promising fuel for usage in fast reactors, and initially it was developed for that usage. Also, another advantage of this fuel is the fact that it can be converted into solutions quite easily. Even nitrides containing more than 20, about 30% of plutonium were easily converted to solution by nitric acid, while it's known that mixed oxide fuel containing 20 or 25% of plutonium is quite inert and can hardly be converted to solution by nitric acid. Also, another branch of fuels is accident-tolerant nuclear fuels, they have started to develop mainly after Fukushima incident, and their aim is to improve the performance of the fuel under accident conditions, mainly local conditions. It means loss of coolant accident. There are two ways to improve the appearance of the fuel. First, it's improve fuel matrix itself, and it can be reached by either doping uranium dioxide with chromium oxide, which improves its thermal conductivity, or by replacing our beloved uranium dioxide with something else, for example, uranium nitride or uranium silicate. And the second way to improve the fuel appearance is to improve the cladding materials of the fuel. So we can either develop new cladding materials from new stainless steels, or we can take conventional zirconium alloys and cover them with inert coatings, mainly chromium coatings and silicon carbide coatings are used. And the main aim of these coatings are to decrease hydrogen generation by the vapor zirconium reaction, which occurred in Fukushima and led to the explosions of the second reactor block. The second, it was the fourth by the counting, as far as I remember, but it was the second to fail. So when we have spoken about fuel metrics, we can speak about how this fuel metrics can be designed to put into the reactor core. There are a lot of variations. There are even more variations in this field. First of all, we should mention the classical fuel design, it's fuel pellets in fuel rods. We produce, the fact is that it's very hard to produce big thing made of ceramics because ceramics is likely to crash, or it's a very ductile material. So small pellets are made and used. These small pellets are harder to break, and we take zirconium or stainless steel rod and fill it with these small ceramic pellets. So then this rod pulled with pellets is assembled into the fuel assembly, and the fuel assembly itself is placed inside the reactor core. There are some issues with such type of fuel. For example, the fuel pellet does not, at first, does not contact directly with fuel rods, and special heat transferring media should be made to transfer heat from pellets to the fuel rod itself. Mainly it's helium gas, so fuel rods, they are not vacuumed, they are not under air, they are under helium atmosphere. And that's all, I suppose. The next design is composite fuel. It's fissile material dispersed in inert matrix. The fissile material itself can be metal, ceramic, and the matrix itself can be metal or ceramic. So there are about 3 main types of such composite fuels, like metal fuel in metal matrix, and this is used in research reactors. Like, as far as I remember, the alloy of uranium with molybdenum is used, and it's placed in molybdenum matrix. The main advantage of metallic matrix is the fact that it can be of complicated form. So if we construct a very complicated core where heat producing elements or heat producing rods or fuel rods should have a very curvy lines, the composite fuel is a perfect choice. So that's because that's why it is used in research reactors. Also, ceramic fuel can be dispersed in metal matrix. And if we speak about ceramic dispersed in the ceramic, it is not widely used. It's mostly studied as a potential replacement for traditional dioxide fuel. And this ceramic matrix should possess like higher thermal conductivity, higher chemical stability to survive the local conditions, loss of coolant conditions. The next interesting type of designs are vibrational package or sphere package. They're quite similar to each other in idea, but different in technology. The vibrational package was designed in Dimitrovgrad, and it was designed to produce highly radioactive fuel obtained from pyrochemical ways of reprocessing. This design was invented to avoid the procedure of pellets making because no one wants to work with highly radioactive contaminated by minor actinides oxides which produce a lot of dust to form a pellet. So as far as these oxides are obtained in particles after the pyrochemical reprocessing, we don't want to press and sinter them. We just powderize them a little bit more, make 7 or 3 size fractions, and simply put these fractions in counted proportions into the fuel rod. The proportions of size fractions and the size of the size fractions were counted in such manner that a quite dense filling of the rod is achieved. Then it's additionally densified by vibration, and we have quite traditional fuel rod, which can be placed in normal nuclear power plant, and which at some cases were placed in normal nuclear power plant, but without the operation of pellet making. About 3 assemblies of vibrational. Yes. As less as we can spare space should be left in the fuel rod. They will mostly be retained inside the particles itself. The particles itself are not the monocrystals of ceramics. They are agglomerates of ceramics, and they have pores. They have grain boundaries at which gaseous phase can condense and can be retained. I also will note that it's a good question because only experimental assemblies were mostly studied, and there is not a lot of information about this fuel swelling and gas retention. But anyway, about 3 fuel assemblies of vibrational packed fuel were irradiated in Ben-600. It was the program of burning down weapon plutonium. And the second type of fuel, sphere-packed fuel, is very similar in its idea to the vibrational packed fuel, but we use the particles not of random not of the random shape, but intentionally made sphere particles made by salt gel, I suppose, method, and they also have several size fractions which are mixed in determined proportions to achieve the highest density possible. But as far as I am concerned, such type of fuel didn't even reach like the full scale irradiation in usual normal nuclear power plant. And another fashionable type of fuel is so-made triisotropic coating system, or TRISA fuel. The main idea of this fuel is to make a fuel rod out of a fuel particle. In order to achieve that, small particles of fuel are made. These particles can be from uranium dioxide, as it is shown in the picture, or they can be made from nitrate, from mixed oxide fuel. Then this particle is covered with a buffer porous layer of carbon. which is made to retain gaseous products and fission products and fission recoils. Then this buffer layer is covered by inner pyrolytical carbon layer, which aim is mostly to protect the kernel, like the fissile matrix, from the atmosphere of silicon carbide deposition. Then we have a silicon carbide itself, and the layer of silicon carbide is playing the role of fuel rod, of a fuel cladding, and it is the main layer that is that counts for retaining pressure inside the tracer particle. And the outer and above the silicon carbide layer, we have outer pyrolytic carbon layer, which aim is to protect silicon carbide layer from mechanical damage. And the main idea of these tracer particles is that they can be either simply mixed with graphite pebble, or they can be included into graphite blocks. And this type of fuel was mostly designed for high temperature gas reactors, gas-cooled reactors. And as far as I remember, one reactor of this type is currently working in People's Republic of China. So you can count TRISO fuel as an ultimate version of composite fuel. And the last very exotic type of fuel is liquid fuel. First of all, in the beginning of the nuclear era, two aqueous reactors were built. They were working on uranyl sulfate solution for about 1/2 of a year in the United States. But there were several problems and issues. Sadly, I don't know what kind of issues and what kind of problems, but they were closed. And the second type of liquid fuel is melted salt or molten salt. Initially, it was designed as a fuel for aircraft reactor, but this project didn't manage to fly, and they gave all the ideas and the schemes to the, like, not commercial, but to the research laboratories. And one reactor working on molten salt fuel was built in the United States, and it worked there for 4 years. As like beryllium fluoride and lithium fluoride eutectic was used as like the main fuel body, and sadly I don't remember what percentage of uranium tetrafluoride was added, but it was working on uranium-235, and at the last year of its working, uranium-233 was added. There are several advantages of such type of reactors. First of all, it has low pressure, unlike power water reactors or boiling water reactors, because molten salt at the temperature of the operation, and it's about 700 degrees centigrade, doesn't volatilize very hard. And secondly, it has negative thermal coefficient. It means that if the temperature in the reactor rises very high, it decreases the density and decrease the neutron retention, and so the power decreases, and there is like no uncontrolled chain reaction can occur. It will shut down itself. And secondly, you don't have to take out fuel assemblies to recycle uranium oxide or other forms of fuels from neutron poisons, or it means that elements that capture neutrons very efficiently, such as rare earth elements. You can make it without shutting down the reactor, just making an additional loop of molten salt that crosses the small reprocessing plant, which cleans away all rare earth elements and other fission products. That's all. Thank you for your attention.
Thank you very much, Mikhail. Maybe someone has any questions? Yes, please.
Thank you very much for the lecture. So my question is about the fuel assembly design. Yes.
This was
Yeah. So what I've noticed is usually for the Russian type designs, they are hexagonal, right? Like the fuel assembly, it's a hexagonal type. But with the American type, it's more of rectangular. Is there any like design process? Like why is it different, or there's no like difference? It can still work regardless.
it's quite a difficult question for me because I'm not an engineer. I can only assume that they for sure cannot be pentagonal due to some crystallographic and symmetry assumptions. I suppose that maybe it can affect the way of the computing like and performing computations for the reactor core. Technically, as far as I think, it's easier to compute some like properties of neutron fluence for hexagonal form, because it's closer to this circular form, which is the easiest form to count something. But anyway, I think that hexagonal form is harder to produce. So maybe in the Soviet Union, they had issues with correct computing procedures for more easier square types. So they made for countings for hexagonal types. But it's only my assumption.
Thank you.
I'm a little bit confused by nitrite fuel. Here. Yeah. Here, is it a real chemical formula or its assumption? I'm confused by oxidation state of uranium in it.
It's a solid state chemistry, and yes, it's a real formula. It's mononitrate of uranium. And as far as the oxidation state of uranium, I will confess I haven't seen works with EXEF's examination of uranium nitrate, but I suppose that sooner in this building one man will make some EXEF's experiments on nitrate, uranium nitrate. But I think it's a quite normal oxidation state, even if we count that nitrogen is in -3, uranium is able to possess +3 oxidation state.
For uranium, as you know, it's unstable +3. It's +4.
Yes,
and
it's unstable,
+6.
and uranium nitrate is oxidizing at air slowly, but oxidizing. It can be stabilized by kinetics of oxidation. Like in highly sintered state, it can be quite stable. It's like manganese in the oxidation state of 5. It is stable in solutions only in very cold at very cold temperatures, but it can be easily obtained in solid state chemistry.
Okay, thank you.
Any more questions?
Thank you for the really nice presentation. My question regards the design of reactor, the liquid metal fast breeder reactors, because it was really a promising and very efficient reactor type. And even though it's not built in more than 2 cases, so what's the reason for that? Because it's such a interesting and efficient, seemingly efficient reactor type.
I'll say that there have been built more than 2 reactors in commercial power reactors. There was one reactor working in France. It was named Phoenix, and the second reactor was also built, Super Phoenix, but it was either never started or it worked not for a long time. Of course, there are several problems, mainly technological problems and engineering problems with this reactor. For example, in Russian reactors, liquid natrium is used as a coolant, and special treatment is needed for such coolant. For example, you don't want it to contact any oxygen, any water. You should take new materials which are resistant towards liquid natrium, sodium. I'm sorry, sodium. And for example, in usual pressurized water reactors like VVR, zirconium alloys are used, while for fast reactors BN, stainless steel alloys are used. Also, I should mention that fast reactors, as far as I understand, are used in as transport reactors on submarines. For example, there is a technology of liquid metal cooled reactor where the mixture of lead and bismuth is used as a coolant. So mainly the problems are of technological and engineering character. And I don't really know how hard it is to count the core of this reactor, because of the different neutron spectrum used, and it has less cross section of fission. So this course should be denser. It has to have the high density of fissile atoms. So there are many uneven problems which arise when people start to build such things.
The challenge is related to corrosion.
Yes.
The corrosion is a big challenge.
So any more questions or comments? No, thanks a lot. So I suppose we can have a small break till 15 p.m., till 3 p.m., excuse me, maybe 5 minutes, just to relax. Thank you.
It's for example, I have 2 reactors, 2 with the same size. For square, I will, for example, this here like this. Yes. So I have a lot of places it's without fill. But in terminal, I can set this places vertices. So I can use a lot of fill, so fill efficiency.
I mean that is you can achieve a denser
Yes.
package of the.
There is number of all.
No, I am not an
I know.
engineer or engineer, so I am not familiar with all these design issues.
I'm designing. Study here.
Нормально. Слышь, может, у него спросить, может, он что-то тогда смотрел? Не водочка.
Dear colleagues, excuse me. We have to be in schedule, so we'll start our next lecture at 15 minutes. Okay? Okay, dear participants, colleagues, please, we can continue our school. And now we have a lecture from Institute of Physical Chemistry and Electrochemistry. Yuri Nivolin, please, thank you.
Thank you. I'm glad to see you on this lecture. And I will continue the topic that was started by Mikhail. And I will tell you about production of nuclear fuel. Okay. I think first we will repeat some information that Vladimir Petrov told you a few hours later about nuclear fuel cycle and the stages that we have in it. There are a lot of stages, and we can try to make our fuel cycle opened or closed. But the first one stage that we can dismiss is ore mining. We need to extract uranium from its ores, and in this process we have, I think, two problems. First one is that uranium ores are very poor in uranium, and the next one is that uranium ores are possess rather high chemical resistance. So because of these problems, we need to chemically enrich uranium product that we have from this source, and also we need to use strong reagents to extract uranium from this source. Typically, two types of leaching uranium from ores are used. First one is heap leaching. Heap is a hill from ore, and we put the solution of leachant to the top of this hill, and we collect the leached uranium solution from the bottom of this hill. To make this process, we need to extract a lot of ore from the Earth's crust. This is not a good idea because we need to make big spheres. Okay, and what we can do, we can don't extract ore from the Earth's crust. We can put our leaching solution by the tubes under the Earth's crust. The uranium will leach, and then from the other type of tubes, we can put this solution to the top of the Earth's crust. We don't need to evacuate the huge volume of the Earth from the underground. Okay, and to do these processes, two types of leachants are typically used. The first one is acidic leachant. When we use acids, and the typical acid to leaching is sulfuric acid. We can leach uranium from different type of ores, including silicates, phosphates, oxide ores, and another. But sulfuric acid is very strong leachant,
And with uranium, we also will leach another metal cations like iron, aluminium, and silicium in form of silica, a lot of impurities. But the concentration of uranium in this solution will be low. And the next type of leachants is carbonate solution. This leachant is less corrosive, and typically we use this leachant for the carbonates ores. And this type of leachant make our uranium solutions more pure. Okay, we leach uranium from the Earth's crust with the leachant, and we have a solution in which the uranium concentration is few grams per liter. And in these solutions, we also have different common metals like iron, aluminium, and another. And the first stage we need to do is to purify these solutions to remove these unused components and to obtain uranium. Typically, we use extraction or sorption processes for this stage. And another stage that we need to do is to concentrate our solutions, because the concentration of uranium in leachant solution is very low. And sorption and extraction processes also help us to concentrate uranium. We can raise the concentration of uranium from grams per liter to tens of grams per liter. And after this stage, we can produce uranium 308. Not so good to make the nuclear fuel, but most of the component in this product is uranium. And this type of product we can put on stock. After this stage, we need the second purification stage. That is also done by extraction or by sorption processes. And after purification stage, there are several stages in the result of them is to obtain UFO6, because the next stage that is very important is isotopical enrichment of uranium, and to make this stage, we need to have a compound in gaseous state, and UFO6 is that unique compound, and we can use it to isotopic enrichment. Let's speak a few words about uranium enrichment. There are several grades of enriched uranium. We know that natural uranium mostly consists from U-238, but fissile isotope is U-235. And typically, enriched uranium for nuclear power plants contains about from 3 to 5% of U-235. But low enriched uranium is uranium with U-235 concentration less than 20%. And the high enriched uranium is the uranium where U-235 is above 20%, and weapons grade uranium is the uranium where concentration of uranium 235 is higher than 85%. Also, when we enrich uranium, we have depleted uranium where the concentration of uranium 235 is less than natural. And here you can see the costs of uranium kilo depends from its enrichment, and you can see that the higher the enrichment, the cost will also higher. Okay, and a few words about methods of isotopic enrichment. There are different types of it, but industrial plants use only two ways now, and in fact only one, that is gas centrifugation, but we will discuss two of them, and diffusion and centrifugation. In gas diffusion, you have a porous nickel tube, and you put a flow of U46 through this tube, and lighter molecules will diffuse through the walls of the tube, and heavier molecules will put strictly strictly to the tube, and this is the way how we enrich our U46. The enrichment coefficient of this method is very low, is about 1.003 on the one stage, and this is why you need to build a huge enrichment plants if you use gaseous diffusion. And this is why nowadays this method isn't used, and the most popular method is gas centrifugation. The core of this method is you have a cylinder with U46 gas, and you rotate this cylinder at a very high speed, and heavier molecules of U46 with low concentration of uranium 235 will go to the outer part of the cylinder, and in the inner part lighter molecules will concentrate, and with some special additions you will effectively separate light U46 molecules from heavy U46 molecules. This technology is rather complicated, but it is efficient, and nowadays all plants of uranium enrichment in the world use this process. And if we talk about future methods, most promising of them is separation by laser beam. This essence of this method is like isotopic effect in ionization of atoms or molecules. You can tune your laser, its wavelengths, by a very small value, and this laser photons of this laser will ionize only light molecules of uranium or heavy molecules or atoms of uranium, and one part of molecules will be in the form of ions, and another part will be in form of neutral particles, you can apply electric field to an electromagnetic combination and separate ions from neutral particles. Method is very efficient, but the problem is that you need lasers with very high output energy, and on the other side, and with very fine tune of their wavelengths, and this is a problem. But small plants that use laser separation were built, for example, in USA, and different isotopic products were produced on this plant. Okay, but the main topic of my talk is fuel production. Let's go to this part. And we will start from the classic material, UO2. UO2 is the most common uranium oxide. It have fluoride type crystal structure, cubic lattice, very high melting point, and rather high density. This is very good for uranium, for nuclear fuel production. And also, what advantages this material have? High melting point, as I said, and thermal stability. This is about that under very high temperatures, this molecule don't dissociate on pure uranium and oxygen, for example, like several binary uranium compounds do. Also, uranium dioxide have good properties for ceramics manufacturing. In the reactor, there are a lot of radiation from neutrons, from fission products, and uranium dioxide have an ability to withstand with these high radiation doses. And also, crystal structure of uranium dioxide is very good because you have cationic vacancies in the structure, and you can put different metals, metal ions in these vacancies, and this is a result in the fact that this crystal structure can include different fission products, because when the reactor works in fuel, fission products are generated, and you need to capture these different these fission products in your fuel. Okay, this is a short scheme of UO2 fuel production. We start from U46 that is enriched, isotopically enriched. We convert it to UO2 material. Then we make an operation of fractionation granulation to have particles of required size. We add the binder to make the process of pressing more convenient. And at these stages, we work with powder. Then the stage of cold pressing is applied. And after this stage, we have a pellet that is called green pellet. In atomic industry, green pellet is a pellet after cold pressing, but before the sintering. And we have green pellets, then we make a sintering of them. After sintering, we make some mechanical operations like grinding and drying. Then we obtain pellets, and we pack them in fuel rods. And the last step is building of fuel assembly from fuel rods. In this scheme, a lot of scrap and dust generates, and we need to recycle this material. This is the row of recycle is this. Very important step. And in each step, a lot of inspection procedures are applied, and we will discuss them later. First step is UF6 to UO2 conversion. Several processes were developed to do this. We will discuss ADU process and AUC process, AUC process. The first process named after ammonium diuranate, ADU, and what is the essence? You have UFO6, you hydrolyze it by water to oxofluoride, and then you add gaseous ammonia or ammonia solution in water, and the yellow precipitate is formed, ammonium diuranate. And the next stage, you reduce uranium in ammonia diuranate by hydrogen containing atmosphere, and you obtain UO2. And another one process called after ammonium uranyl carbonate, AUC, AUC. The essence is you add water vapor, ammonia gas, and carbon dioxide, and this carbonate insoluble complex is formed, also yellow. And at the next stage, you reduce uranium from uranium-6 to uranium-4 in dioxide by hydrogen containing atmosphere. In fact, sometimes this process done not in one stage, but in two. For example, first you calcine this compound in air, and you obtain U3O8, and then you reduce U3O8 by hydrogen to UO2. Different ways are possible. And the result of these processes is UO2 powder. And from this powder, we can start to make pellets. And what is important that slight change in temperature of reduction or amounts of compounds is in gaseous phase strictly influence on the properties of UO2 powders that we obtain. And this is why in these processes you need to have a good model of them, and you need to have many experiments with different conditions to make UO2 of the good with good properties. Okay, we made UO2 powder, and then we try to make pellets from it. On the first stage of fractionation, we separate only particles with 400 or 600 microns in diameter. Also, we can use granulation to make particles of desired size. After that step, we add a binder. Typical binders that we use is zinc stearate or polyvinyl alcohol. And this binder is required to cold pressing. It helps us to make dense green pellet after pressing. The pressure of pressing is like this, and the density of the pellet is about half of the theoretical available. Why also we need particles with these narrow sizes? Because this is also influence of the influence on the stage of pressing, and also you need particles of this size because there are many operations where powder flow in tubes to your equipment, and this flowability is good only when special size of particles is in your system. Okay, we make green pellets after cold pressing. Then the next stage is sintering. We sinter our pellets in reducing atmosphere. Typically, this is the mixtures of argon and hydrogen. High temperature is used, and after this stage, the pellet will have a density that is close to the theoretical one. After this stage, pellet is hard, and we can do mechanical operations with it. For example, grinding. And as you can see, the dimensions of pellets are strictly controlled. For example, the diameter that is closely that is strongly influenced on the gap between the pellet and the rod wall, and this is why you need to very carefully inspect your pellets. And for example, on the quality control stage, up to 20% of pellets will be defective, but it is not very bad because we can take this scrap and recycle it to the head of the process, this stage. Okay. Some additions can be made on this stage. For example, for some purposes, oxides of lanthanides can be added. For example, gadolinium or erbium oxides. This is these additives helps us to make the initial reactivity of the uranium fuel low at the start of or at the start of reactor, and these dioxides or these oxides with the concentration of less than 10 mass percent can also be added to the initial UO2 powder. Okay, we make our pellets, and then we need to make a fuel rod from them. This is a typical view of the fuel rod from the WBR reactor. It has several parts: circuloid cladding, end plugs, U2 pellets, and the spring. And on the next stage, we put our pellets into the fuel rod. Then we put a spring, and then we weld end plug by the electron beam welding. And at this stage, we need to control. And also helium gas is put inside the fuel rod, and several inspections are made. And for example, we test the leakage of our fuel rod by helium mass spectrometry at room temperature or at temperature that is equal to the operating, for example, 300 degrees centigrade. Okay, we make a fuel rod, but fuel rod is very thin and long, for about 4 meters long and 10 millimeters in diameter. And it is flexible, but we need to make strong device from fuel rods, and this device called fuel assembly. So typical Russian fuel assembly is shown at the bottom of the slide from the WBR reactor, and it has a top nozzle here, bottom nozzle here, fuel rods in fuel assembly, grid in which fuel rods are inserted, and also guided tubes in also for fix of fuel rods. In our country, 2 plants manufacturing these fuel assemblies, one near Moscow and another one in Siberia. Okay.
Some gas is added.
Yes.
Is that depressurization prevent fuel cladding interaction, or is it for thermal conductivity?
Several for thermal conductivity, yes, because helium is a good thermal conductor, and also you need an inert atmosphere in your fuel rod, because if you have air, uranium dioxide will oxidize, and it is not good. And the third one is, what about leakage test? Yes. Yes, it's an additional. And the fourth is that if you put a helium at high pressure, you can compensate with this technique the pressure of water when your fuel pins, fuel rods works in the reactor. This is another option why you can put gaseous helium. Okay. I think that we briefly discuss U2 fuel production, and then we will discuss, I think, similar fuel, but in production it is rather complicated. Let's discuss MOX fuel pellets. And first we discuss dry road. MOX fuel, as Mikhail says, is a mixture of uranium and plutonium dioxide, or mixed oxide. And to make this mixture, several methods can be used. And the first one and the most popular is mechanical blending. You have UO2 powder and plutonium dioxide powder, and then you put them in ball mill or another milling machine, and you mill them together a long time. And after this blending, stages that you will apply are similar to uranium dioxide fuel. Typically, plutonium content in this fuel type is 20% or lower, and the rest is depleted uranium. You need intimate blending of dioxide powders because inhomogeneity in plutonium distribution is strongly affected on the fuel work. And due to the presence of plutonium, you need a higher automation of production because plutonium is highly radiotoxic material, especially dust particles. And also, if you work with not weapon grade plutonium, but with plutonium discharged from nuclear power plants, in this material, americium 241 concentration will be high, and gamma rays from these radionuclides are very strong. This is why MOX fuel production need to be very high degree of automatization, and this is why the cost of these plants is very high, and the technology is rather complicated. Another special thing that you need to control oxygen potential during sintering. When you sinter uranium dioxide fuel, you don't need to control this value, but with MOX fuel it is important because MOX fuel have a tendency to form not a stoichiometric dioxide, but oxygen deficient. For example, with Brutta formula like uranium, plutonium, or 1.97, for example. And this is not good because dioxide with this non-stoichiometric dioxide will interact with your cladding, and if we need to control this Brutta formula by control oxygen potential use sintering. For example, if we use hydrogen containing atmosphere, we need to add some water vapor in controlled amount, and after this step we have a fixed oxygen potential. Another feature of MOX fuel is that dioxides of other actinides can be added. For example, in Russia this year 3 MOX fuel assemblies containing americium and neptunium were made and were loaded in BN800 core to test them. Okay. Historically, the leader in MOX production is France, and in Belgium there is also a plant. But in Russia nowadays also there is a big plant of MOX fuel production in Siberia, in mining chemical combined plant. And this plant produces MOX fuel for BN fast sodium reactors. As I said, the critical part in MOX fuel production is intimate blending of uranium and plutonium powders. And for chemists, the first thing how to improve it is that can we chemically convert it together? And yes, this is called wet rod. For example, we can use the solution of plutonium and uranium nitrides, and we can add a precipitation agent, for example, ammonia and carbon dioxide, and after that, insoluble carbonate complex will produce. And in this complex, uranium and plutonium are mixed at atomic level, and we have a good homogeneity without mechanical blending. So we can reduce this complex by hydrogen-containing atmosphere and to obtain mixed oxide very easily. But the problem of wet processes is the generation of radioactive wastes in big quantities. But I think in future these processes will be developed more, and maybe mechanical blending will be replaced by chemical coprecipitation. Okay, another type of fuel that is rather similar to MOX fuel is remix. This type of fuel was developed in Russia for thermal neutron reactors. The essence of this fuel is you have mixed uranium plutonium oxide from reprocessed spent nuclear fuel of thermal neutron reactors with the concentration of plutonium typically about 1 or 1.5%, and you add fresh and enriched UO2 powder to this mixed oxide, and blending them and make a new fresh fuel at the technique that is similar to MOX fuel production. Despite the concentration of plutonium is much lower than in MOX production, high radiotoxicity is also there is a high radiotoxicity of remix fuel production is, and this is why you need the plant same as for MOX production, And in Russian Federation for remix fuel, also MCC plant for remix fuel production, MCC plant is also used. Okay. Let's go to the next type of fuel, fuel that is based on uranium nitride. In Russia, it is called MNUP. Mixed nitrides uranium plutonium. Abbreviation is. The first stage that we will discuss is the synthesis. At a large scale, typically uranium nitride produced by carbonitridation scheme, and in this scheme we have UO2 powder, plutonium O2. We mix them with carbon black. As in MOX fuel, we need a very intimate blending. Then at high temperature, higher than 1400 degrees centigrade in nitrogen flow, we will obtain mixed uranium plutonium nitride, and carbon will be in the form of carbon monoxide. But the real process is rather complicated. First, you heat your initial mixture of dioxides and carbon black at, for example, 1600 degrees in nitrogen flow for several hours. Then you replace nitrogen by the nitrogen and hydrogen mixture to remove the excess of carbon black. And then on the stage of cooling, you change the nitrogen containing atmosphere to the argon flow, because if you don't do this, you will obtain U2 and 3, because UN is thermodynamically unstable in nitrogen at the temperatures below the 1600 degrees centigrade. Typical carbon to metals ratio varies from 2 to 3. Intimate mixture of oxides with carbon black is required. You need to blend your mixture in ball mill, for example, 24 hours. Excess carbon is removed by hydrogen in this step, and cooling in argon flow prevents the uranium sesquinitride formation on cooling. Okay, we obtain mixed uranium plutonium nitride powder. Then we need to make pellets from this product, and this is the sintering stage. At this stage, we make uranium plutonium nitride green pellet by cold pressing, and then we heat this green pellet at very high temperature, about 1900 degrees centigrade in nitrogen flow. And also on cooling stage, we need to replace nitrogen by argon to prevent the U2 and 3 formation. Some problems are at this stage. Nitride green pellets are fragile instead of dioxide pellets, for example. And this is why you need to carefully move them to your furnace. And this is the photo of the device that is used in Russia for that purpose. A special machine with air evacuation, bring the pellet, and can carefully move it, put it Okay. You need very high sintering temperature because of low uranium diffusion in uranium nitride. And this very high temperature also is the reason that you need special materials for furnace and sintering equipment. Technique is very complicated, and another problem for all nitride material is this is very air sensitive material. You need to do all mechanical operations in argon atmosphere. And nowadays in Russian Federation, small plant that will produce uranium plutonium nitride fuel is under the construction, also in Siberia. This is a photo of furnace for the sintering, and you can see the glove boxes that later will be filled in argon, in which different operations with these pellets we can do. As you can see, the furnace is very big. Okay. The next type of fuel that we will discuss is tracer. Very interesting conception. First, we will discuss the production of kernel of U2 that is in the center of the tracer. Two ways how to do this kernel are available. First is internal gelation. You need to swap this. External gelation is here and internal is here. For external gelation, you have uranyl nitrate solution, and you add to it polyvinyl alcohol and ammonia, and then you make drops with a special size. And if you mix ammonia and your uranyl nitrate solution, ammonia diuranate precipitate will form. Another way to make an ammonia diuranate precipitant is the use of internal gelation. Also, you have uranyl nitrate and this source of ammonia. And when you mix these reagents and drop them in hot silica gel, you will also produce ammonium diuranate. After this stage of dropping, spheres, yellow spheres like this are produced. And the next stage is aging and washing. And the product of this stage, then calcinite. And we have UO3 particles. Then we reduced these UO3 particles by hydrogen to UO2. And on the stage of sintering, we will obtain UO2 kernel. Method was developed in 1917s, I think, or 1916s, and by this method you can obtain not only uranium dioxide kernels, but uranium nitrides, uranium carbides. Universal approach. Okay, we obtain the U2 kernel, then we need to make layers on it. How we do it? The first stage, the first layer that we will deposit is a low density pyrocarbon. We use chemical vapor deposition to do it. We expose our kernels to the mixture of acetylene and argon in a furnace like this, and after that a low density pyrocarbon layer is formed. Then we change our gaseous phase to the propane, and after that high density pyrocarbon layer is formed. Next gas phase is organic silane, and the result of it is a silicon carbide layer. And the last step is propane. After that, we have high density pyrocarbon layer. And the final, in final, we have tracer particles. Nowadays, in Russia, there is also interest in this type of fuel, and ENM Institute in Rosatom develops the technology of fuel elements with tracer fuel. Okay, and the last type of fuel that we will discuss is a metallic fuel production. We will discuss the production of dispersed fuel, where the fuel particles are inert in metallic matrix. First type is the silicide fuel dispersed in aluminum. Typically, U3C2 compound is used, but sometimes U3 silicon also is used. The first step is alloying of uranium metal and silicon, for example, using arc melting device. After this step, you have a uranium silicon silicide ignite, rather fragile material. After the crushing step, you will have this silicide powder. Then you mix it with aluminum powder, and after the hot and roll step, you will have a fuel plate that looks like this. Small particles of silicide powder are in aluminum matrix. I think that this type of fuel is we can call kermet, because silicide is ceramics, and aluminum is metal matrix. And next type of fuel is metal. We use uranium 10% molybdenum alloy. This alloy stabilizes uranium in gamma phase. This is why you can easily roll these alloys, and other mechanical operations are easier than with uranium in alpha phase. So first you alloy together uranium metal and molybdenum, for example, by arc melting. You will obtain alloy ignites, but then you need to disperse them in powder. But for molybdenum fuel, it is not so easy than in comparison with silicide. You can use grinding as one option, or you can use melt atomization. Melt atomization is a process in which you have a disk that rotates at very high speed, and you drops droplets of your alloy on this disk, and disk will disperse your droplets to the small parts. Melt atomization. And after this stage, this is a mistake. After this stage, you will have a uranium molybdenum alloy powder. You will mix it with aluminum powder and hot roll, hot and cold roll. You will have fuel plate that looks like this. Okay. I think I finished. Thank you for your attention and some useful literature for you.
Any questions? No questions at the moment. Okay. Yeah. I think many questions were during the lecture.
Thank you for the nice presentation. You mentioned that the MOX fuel, that americium and neptunium oxide is also added. Is this some benefits for the production of energy, or is it merely a reprocessing or transmutation process of this element?
Minor actinides can be added to MOX fuel to transmutate them, and this is a reason to make this fuel, because for for reactor campaign, this is not very good additions. And
so there is no additional energy production with this actinides. It's only for transmutation. Yeah. Any other questions? Yep.
So thank you for the presentation. My question is about the laser enrichment. So for Silex, I think it's one expensive and then not quite a very difficult process, but it's not widely used. Because of proliferation, it's faster to enrich uranium with laser. So aside that, and then from research, it seems the US are trying to decrease the use of that process. So in Russia, is it in use like to enrich uranium, or you've like banned that process? Because it's quicker to enrich uranium with the laser enrichment process.
I don't understand about
Обогащение лазером.
benefits.
В России рассматриваете?
I think that yes, several scientific groups works on this process, but the amount of gas centrifuges plants in Russia is enough. 6 plants are now in operation, and nowadays there is no enough reason to implement laser technique.
If there are no more questions, then let's thank our speaker again. And we have a short break now, and I have your presentations with me, and we will start in 10 minutes, let's say, with your presentations.
Oh, this one. We have one mic. Thank you.
I need to stay here. Yeah, so it's so scared. Stay. Hello, guys. Thank you so much for everything. Thank you, University of Moscow. Thank you, committees. Thank you, all my colleagues. I am very glad to stay here today. My name is Fabio, and I'm from Brazil. So far away of here. It's a beautiful place in tropical hot place. So I stay with difficulties with in so cold in Moscow, but I'm very excited to know this beautiful city and connect with my colleagues too. So I work in the Radiopharmacy Center in the Research and Development Department in Nuclear and Energy Research Institute that stay in São Paulo City and São Paulo State too. I am a biologist with a master in biochemistry, and I do my PhD in nuclear technology too. And I would show some examples that work that you stay doing my institute. I study a lot oncology and the neuro disease, and we radiolabel some molecules like antibodies, like pectins, like small molecules, aptamers, and peptides, and you user to understand the process or bioavailability or biodistribution and pharmacokinetics of these molecules. So I don't have time to explain more, but if someone has a question, please ask me. And this is other example about the translation studies that you do using gallium 68.U bixidine for diagnosis of infections process, like we can see here. And the other example is the radiolabel bioavailability and biodistribution of nano-encapsulated anthocyanins in the rats too. So this is a few example about my background. And again, thank you so much for inviting me and hosting me. I'm very glad to stay here and know this beautiful city and this beautiful university. Thank you so much. Any question?
Do you have any questions? I think we will have time during our evening in more relaxed atmosphere. So, just to check. Okay. Okay. Omar. Something new, maybe.
You change my name. Hello, my name is Omar. I'm from Egypt. In 2022, I finished my specialist degree in nuclear power plant design and operation engineering from Tomsk Polytechnic University. In the same year, I beginning my master in 24, I finished my master degree in nuclear science and technology. And in 24, I'm study PhD in focusing on VVR technology and Atom Technical University too. And also I'm a member in Rosatom project, Russian Nuclear Education Ambassador. That's all. Any question?
Thank you. So, next one.
Hello, everyone. So my name is Knight Anokwa Yeboah. I'm from Ghana. And so my academic background, basically, currently I'm a master's student at the National Research Nuclear University in Obninsk. And I'm in the field of nuclear physics and technologies. But mostly my major is in radiation safety and ecology. So I had my bachelor's with honors from the same university and in the same field. So next. Yes, so professionally, I don't have much of experience. I've worked only a year. After my bachelor's, I went back to my country, Ghana, where I worked with the Nuclear Regulatory Authority in Ghana. So basically, it's the boring stuff, just the laws and the requirements and regulations. So my goals is to work in the nuclear security, basically the non-proliferation and international relations aspect, where we try to curb the nuclear, production of weapons and everything. That's my interest for now. And so the question is, why this field? Why do I really want to be in this professional career? So I'm passionate about the peaceful application of nuclear energy and technologies in Africa and the world at large. And I also believe that nuclear energy can play a very significant role in Africa's economic development in providing reliable source of electricity that can power industries, create jobs, and improve the quality of life for millions of people. Oh, it's not visible here, but yeah, these are my contacts in case of anything. I'm on almost all the social media platforms. Thank you very much.
Not yet.
So, hello everyone. I'm Hipatullah Abdul Hakim, and I'm from India, the southern part of India, and I'm a third year medical student. Third year medical student in MEFI. So there is nothing. Most of the people they have achieved. So I'm in the process of achieving. And I need to say some words to Fabio. That presentation was really good because everything that is based on our daily life nuclear applications in medical life. So it's based on treating cancers and other types of testing MRIs and PETs all comes under this nuclear facility only. So that for that I can't know about how the waste is generated, and I got to know many information from this, and I'm really glad and I'm really committed for that, and I'm really thankful for the Department of Chemistry and other who are this program, and it's really nice to be here.
Thank you.
Thank you.
Hello everyone. My name is Nguyễn Tung, and you can call me Tung. And I am Vietnamese, and I come from Vietnam. And currently, I living in Moscow, Russia. And about education, I got bachelor degree in the field of nuclear technology at the Orkney Institute for Nuclear Power Engineering in Orkney, Russia. And now I am the second year master student study in National Research Nuclear University, MIFI in Moscow, in the field of chemical technology. I can speak Vietnamese, English, and Russian. And recently, I have experience in student internship. The first company I have internship is scientific compliance in Moscow, and it is about the extraction of medical plan. And the second experience is that I have internship in endocrinology research center in Moscow, and it's the place I will write my thesis about the quality control of radiopharmaceutical specifically in 1999 and technetium unix PSNA. I have short-term aspiration. The first, I wish that I can pursue a PhD or join in major scientific project. And the second is my wish when I come again in Russia to miss Vladimir Putin, because I never see him in the real life. And the last one is explore the future collaboration or practice opportunity in with Rosatom. Thank you for your listening.
Olga. Yep.
Hello, guys. My name is Olga. I'm from Belarus, Minsk. I'm from Belarusian State University. I finished it at 2020. Then I started my master degree. And I studied radiation chemistry for radical transformations of some organic substances, radiation-induced transformations. And for several years, I was working as junior researcher and teaching assistant at this university. We have a department of radiation chemistry and chemical pharmaceutical technologies. And I also am honored. I'm also honored to be one of the fellows of Marie Skłodowska-Curie Fellowship by IAEA. It's the program that supports women in nuclear. By the way, did you notice that we have just 5 women here in the room? Because I know this IAEA will not like this. But now I'm just 1 month. I work at another place. It's a nuclear research institute in Minsk also. The full name is Joint Institute for Power and Nuclear Research Sosny by National Academy of Science of Belarus. And also, I made a special slide for me and international schools in MSU because it's my first school. And I'm very happy to be here again. And because these are the favorite events by Rosatom. And I also, I'm very happy to present to Olga. Look, I have your photo. Yeah. I have 3 photos from 3 previous schools, and I hope to have one more from this one. So, thank you.
So now we have a Belarus team. So now Artyom. Next will be the team of the 6.
So, hi, let me introduce myself. I am Artyom Maliborsky. I'm a lecturer in Belarusian State University, and currently I'm working in Department of Chemical Pharmaceutical Technology and Radiation Chemistry. So, I graduated from Belarusian State University in 2019, got my specialization in chemistry of high energy, then I finished my bachelor or master degree, and then go to the PhD studies. Hadn't completed it yet, though, but I got a lot of working experience with chromatography, radiation chemistry, and radiochemistry. So what I was doing all these years in Belarusian State University as a researcher and a lecturer. So it's like idea department. My research work was to reduce some complex biological processes to the fundamental radiation chemistry ones, and to study their fundamental characteristics like reduction potentials, kinetic constants, or like products of their interaction with different substances. Why do we need it? As, for example, to develop new pharmaceutical drugs or radiosynthesizers. As in my case, as I'm working on nitro-containing radiosynthesizers in Belarusian State University. So that's all. Any questions?
Thank you. And now I don't know how you will do it. Six people. You can stay in here, yeah.
Это встану вот просто. Да.
Так, а что не подсунуться? Давай, подползай.
Тебя не будет видно.
Не будет видно, да.
А, сильный.
Так, да, все. Good evening, dear colleagues. My name is Alexey Yakas, and my fellows are students of Belarusian State University, Chemistry Department, and in the slide you can see our names.
Okay. Yeah. This is our chemistry department. We are from, as my colleague has said, we are from the Belarusian State University. There are 6 of us. 3 of us study fundamental chemistry. 2 of us study chemistry of high energy. It's like more like radiochemistry probably. And me, I study pharmacy. So we hope to get many connections there, because a few years prior in our country there was a start of the new nuclear plant, and we hope that we can exchange experience with the experts that we could see at the school. We hope to make new connections because you know our professional life only starting. So yeah. Nice to see you all. Thank you very much, Olga.
Well, I think it would be nice if my fellow colleague introduced himself first. Kind of forgot. This is Yegor Tatarinov, for those who don't know. And, I'm Pavel Lashkevich. Well, as Yegor already mentioned, one of the reasons why we came here is the fact that, well, recently, like in 2020, nuclear plant was launched in our country. So, well, it would be nice to study different methods of processing spent nuclear waste, nuclear fuel. Sorry about that. and study methods of detecting radioactive elements and separating them. Well, that's it, I guess, on this point of concern.
Yeah, that will come a bit later. So my name is Mikhail Yafeyev. I am a student, obviously. I also do some research work in National Research Institute of Physical and Chemical Problems, I guess would be the translation, in the laboratory of nanochemistry. So yes, so we came here hoping to gain new practical skills. We'll have laboratory work. That's great. Really looking forward to it. Deepen some, not some, all knowledge in the sphere of spent nuclear fuel because as Pavel already said, it is a rather concerning point for our country in general because we have a working power plant, nuclear power plant. Yes, I don't know what else to tell you. Generally, my interest in the topic was piqued when I read the book. I don't remember the name of the author. It is called Driving the Nuclear Reactor. An English guy wrote it. It is basically a
popularization.
Yeah, it is a popularized version of a manual for a guy that pushes all the buttons on the power plant. It is basically it basically told me about what does what and how it all works and comes together. Yes.
Thank you. My name is Kirill Tsikhamirov. Yeah, I a student of BSU. Well, yeah, and my yeah. My major is high energy chemistry. Yeah, and also I work at the laboratory of X-ray crystallography. Yeah, and all says that, and I say it's true. Glad to hear this here. Yeah, to be here. Yeah, and thanks.
My name is Arjun Lavrov. My major is chemistry of high energy, and in conclusion, I'd like to say that в целом большая благодарность.
For this opportunity to come to the Moscow State University and to participate. Such a wonderful event. That this collaboration will be fruitful. Because you can use it.
Так и понял. Ну все, на этом
Yes,
хватит.
it's depends on you for your attention.
So we stopped with Artyom and now Aditya. Aditya. Yeah.
Yes, hello everybody. This is my second time in Moscow. The last time I was here for a summer school. This year I wanted to see the winter in Moscow, but Olga is saying that this is not too cold. The average. So, yeah. So a little thing about me is I have studied nuclear engineering after my undergrad studies in mechanical. My master's was from France, and I specialize in nuclear waste management. Currently, I work at an university in India, which runs a few courses on nuclear. So I take those courses remotely. Apart from that, I've visited a lot of conferences around the world. You can say I've been to US in August, and now this year this is my second conference. I wish to pursue my PhD later on in the field of nuclear waste management, possibly explore options regarding the repository and the storage of nuclear fuel. Apart from that, I tend to do some adventure sports. The first photo is not adventure. I was just pushing my cycle. But yes, yeah. Thank you.
Thank you very much. Thank you.
Good morning.
Yeah.
Okay, nice to meet you. I am Mohammed Boujiza. I am from Tunisia. Temperature now in Tunisia is 20, not -1. In Tunisia, I want to say that we have the oldest university in the world. It's Zaytuna University, and it's founded at the end of the 7th century. Yes? What? No, no. Okay. Okay. I received my biomedical technician diploma in 2004, specializing in nuclear instrumentation, that's the linear accelerator, cobalt 16 machine treatment, gamma camera, PET scan, just like this. After that, I graduated on engineering in biomedical technology. In 2023, I completed the research master's in biophysics, radiophysics, and medical imaging. Now I work as a technical manager of the laboratory of University Hospital Ibn al-Jazar in Kairouan. Nice to meet you another time.
Thank you.
Thank you. That sounds great.
Yeah.
Should I? Hello, good evening to everyone. So my name is Siti Khadijah binti Muhammad Fauzi. First of all, I would like to thank to OGA and Radiochemistry Division for giving me this opportunity to join this winter school. So let me introduce a bit of Malaysia. I'm from Malaysia. So from whole this world, so Malaysia is over here, Southeast Asia. So it's just want to let you know, in Malaysia we have multiracial races. So we have Malay, Indian, Chinese. So and our most popular foods in Malaysia is teh tarik, which is a milk tea, and also nasi lemak. It's a coconut rice. So if you have the opportunity to come to Malaysia, so please have these foods over there. So some brief about me. So I was born in Johor Bahru, Malaysia on December 1989. So I'm graduated from local university, bachelor in pharmacy. So in 2015, I started working in nuclear medicine department in one of the government hospital in Malaysia. So currently, I'm pursuing my master program in this university, master in radiopharmaceutical chemistry. And actually, this is my first time meeting my professor here, Professor Vladimir Petrov. So yeah, this is my hospital where I'm working before. So I've been working here since 2015 until last November before I come here So basically, I'm working with the nuclear medicine department. So we have physicians, nurses, the technologists, radiographer working together. So most in our department, we are doing diagnostic imaging, SPEC and PET. Sorry, we only do SPEC imaging because in my center we don't have PET camera. And also therapy for thyrotoxicosis. And actually, yeah, we have 3 radiopharmacies there. And the guy over here is my senior, who the one encouraged me to continue this master program here. And he's the one that suggested me to come here and continue my master program. Sorry. Looking at the theme of this school program, I think even though it's not like niche to specific to my field, but I hope that I can gain as much knowledge and experience from this school and to explore new horizon of education from many experts here, and hopefully to make new connection with all you guys. And this is my contact. That's all. Thank you very much. Yeah, thank you.
Of the world that establishing connections, new connections, one of the advantages you can take in here. So please feel free to, to discuss it with each other. Feel free to address to the staff of the division, right? Ask questions. Okay.
Is it your painting? No. Okay.
Thank you. Hello everyone. My name is Sauliet Adresheva. I'm from Kazakhstan. Originally, I come from east part of Kazakhstan. My hometown is Uсть-Каменогорск, but now currently I live in Almaty. Almaty is the second biggest city in our country, and I'm a junior researcher at the Institute of Nuclear Physics, is located in Almaty. And with respect to my education, my major is chemical technology of inorganic substances. I graduated from Satpayev University in 2018, and I then completed my master degree in the same university from 2018 to 2020. And Satpayev University is one of the biggest and the first technical university in our country. And some international courses I attended, and okay. Moving on to my experience, my professional career began in 2018 as an assistant at Satpayev University. Then I worked as an engineer at Institute of Chemical Sciences, and since 2021 I've been working at the Institute of Nuclear Physics at a laboratory of nuclear physical methods analysis methods in the Center for Integrated Environmental Research. And the main focus of our center is doing radioecological monitoring, and my current role involves radiochemical preparation of water samples to determine uranium isotopes, and I also conduct gamma spectrometry to identify radionuclide consumption in environmental samples. And today I'm here to dive deeper in radiochemistry and enhance my knowledge in this field, and also find new colleagues and friends to make new contacts and find new like-minded people. And thanks to organizing committee for the opportunity to be here. Thank you.
Maybe you join the school, right? You can get better quality with the background, with the different, and maybe you will establish, a good school, right?
Good evening, everyone. My name is Ilona Matveeva. I'm from Kazakhstan as well, but I didn't know before that Sauli will come. So today in the morning, we just got to know. So I'm Deputy Executive Professor at the Head of Laboratory of Radiation Ecology at Al-Farabi Kazakh National University. We are much younger than you are. Our university is only 90 years this year, and our laboratory is about 22 years only. So general information about Kazakhstan. So we are located here. So we came from here. So Kazakhstan has 12% of world's uranium resources, and in 2025 produced about 21,100 tons of uranium. I will not read all this. So Kazakhstan is one of the leaders and leader in the production of uranium. So we have a lot of mines and a lot of problems connected with this. And just recently, just in 6th of October this year, we had a referendum about the construction of nuclear power plants. So being a leader in production of uranium, we don't have nuclear power plant up to now, but we plan to construct. And about 71% of our population decided that we should have nuclear power plant. So in laboratory from which I came, we are actually a laboratory inside the university. So we are working only with natural radioactivity, with norm, but with low background radioactivity. So with the equipment which we have, so actually we have alpha spectrometer, gamma spectrometer, beta spectrometer, so we can do measurement. We are working with natural sources. And we are doing different types of scientific projects, and we are open for new projects. So the main scope of our laboratory is radiation monitoring of natural water, soils, bottom sediments, rocks, etc. Carrying out work on radiological monitoring, using different radioisotope methods to study migration of radio elements, and also organization of different courses for people. Thank you. These are projects which we had. And which we have now, and is it.
Thank you. It's interesting that you have a project from the World Bank. Yeah, so okay. Yeah, interesting. Carlos, Sebastian.
Thank you, Professor. Thank you, Olga. I'm Sebastian from Bolivia. I would like just to say that this opportunity I'm here is very important for me. And I think if I contribute to my country also, it would be an important experience for my country, because every time when I started working in the Bolivian nuclear program that started just in 2015, so I was part of the main group to start a project. Now we are developing the project, but we had many difficulties, issues in different aspects. So I would say that I'm more a specialist in developing projects, but technological or scientific projects. So it's very hard, but right now we are trying every day to support these projects. So it's a great experience again, and I am really happy to be here and to be part of this great team. Thank you.
Oops. Good. Yep.
Hello, everyone. Thanks for this great opportunity to be here. My name is Matyás Fodor, and I come from Hungary. I'm a PhD student at the University of Debrecen, Hungary. I'm also a radiochemist working at the Institute for Nuclear Research in the same city. I'm a PhD student since 3 years now, been a radiochemist since 2 years now, and my topic of research is the production of PET radiometals, namely gallium-68 and various terbium isotopes. My expertise includes cyclotron production and purifications of these radiometals, as well as radio labeling and doing various analytic works with them. Here you can see our research team. The Institute for Nuclear Research is home to mostly physicians. This is our little group of 3 radiochemists and 2 technicians. My work experience includes work in a wine laboratory, as well as Helen Egyik Ltd, which is a Hungarian energy drink producer, and as well as working as a nuclear chemist. And for 1 month, I've also worked in the medical imaging clinics with the gallium-68 that's generator produced, just to compare it. Here's a list of notable experiences and conferences I've been to, with the most important ones to me highlighted. I'm 28 years old from a little Hungarian village called Egerszalók. I have various hobbies, and aside of a radiochemist, I'm also an apiarist, which means beekeeper. And I think it's funny how those two come together. To make this... Really? Thank you. Nice. To make this little presentation more interesting, I've included some pictures from my country because I realized that many of you might even not heard about it before. This is our capital city, Budapest. This is Debrecen, the city where I do my work and where I've been living for almost 10 years now. This is Eger, a bigger town near where I live with a castle. And this is a salt mound from the thermal bath in Egerszalók. This is the biggest thermal bath in Central Europe. And this is also Egerszalók with some very old style houses that were dug into the tough rock. And thank you very much for your kind attention. If you have any questions, I welcome them.
I'm Pratham. I'm from India. I have done my higher education from India, and now I'm doing my medical studies. I'm in second course in my finish. So I am 20 years old, and I was born and lived in Punjab, India. I have not much achievements till now, but in future, I hope. Thank you, everyone. Thank you for the organizer committee to have me here.
young lady, in fact. Let me be her ambassador. In fact, she's not with us today. We should register, sorry, not the one, that you gain from the hotel, but her own one. So she studies currently in MIFI, one of the divisions in the Moscow suburbs, in fact. So I believe we just can click on her presentation, and I hope that she will join us pretty soon, right? And she will impact tremendously to the group. And, I hope that maybe tomorrow we'll be happy to meet her if she solves all of her issues with her registration. So her name is Miron, and she's from Ethiopia.
Good evening. I know you are very tired and try to. This is my trip. Says you are very tired, and I try to very. Okay, my name is Jawad, and my last name or surname is Karimi Sabet. My major is chemical engineering. I was born in 1973 in Tehran, and as you can see, I graduate BS, MS, PhD, all in the major of chemical engineering. After I take my PhD, I was joined to the Atomic Energy Organization of Iran and start my activity in the field of isotope separation. Is this my major of field? During of the isotope separation, we develop some method I try to say in the next slide. Beside of my scientific activity, I have some manager activity and experience, but because of lack of time, I skip them because I think focus on the research interest. Well, I focus in two general fields. The first is in the policy making in the nuclear innovation is my major field in the management. As you know, I work in the standardization department in the Atomic Energy Organization of Iran, and we try work on the innovation and technology strategy mapping and how we can implement in the government organization. It is so difficult because this phrase and this term is the most of time used in the private company. And when we want to implement this term in a company or organization is the government, we must change everything. We must looking for public value and other things is so difficult. And one of the things I interested know to Rosatom what we do about this field. And as I said, my main activity is stabilized isotope separation. I work in the gas centrifuge, cryogenic distillation, membrane distillation. The main is gas centrifuge, but beside of them, non-conventional method. We have a lot of activity and research in this field, and you can find my publications related to this field. During of this item, just this item, we graduate about 30 PhD students and also about 50 MS students. Is joined with the University of Tehran University and Sharif University, but in our laboratory in the Atomic Energy Organization. Well, now we focus on the stabilized isotope in environment study, as you know, is very important in climate change, isotope hydrology, and monitoring of the environment, pollution monitoring. This is the new, we are trying to build capacity in the Nuclear Science Technology and Research Institute. Also have some project with the Atomic Energy Organization. At the new field, we about 1 year I work and focus on this is the simulation became, as you know, simulation is less expensive. And when became old, we cannot doing experimental in the laboratory and want to go on the computer. It's very new field, multi-scale, and we have a good team, about 5 postdoc and about 10 PhD students working in this team. And I supervise this team, and we try to simulate the fuel under irradiation during from quantum calculation until CFD, computational fluid dynamics. We start to work about 1 year, and we go about this good situation, and maybe we have participate in some conferences. Another thing, the numerical analysis is, and the supercritical fluid was my PhD thesis related, and as you know, one of the solvent, green solvent in the reprocessing is supercritical fluid, but not yet is not conventional, but we is on the research. From this topic, we have publication, I and my most student, about 150 scientific research articles is good, and also about 100, more than 100 about particle in the national, and also have some books in this chemical engineering, thermodynamics, separation, and also other in the nuclear related on the isotope separation method. Well, according to our activity, I have a National Medal of Research from the Iranian presenter related on the work on the gas centrifuge. Well, thank you for you and your colleagues, and I hope enjoy. Okay, thank you very much. Okay, thank you.
Thank you.
Thank you.
Hello, dear participants and organizers. I'm Valeria, and I'm from Belarus, from Minsk. I'm a first-year master's student at the chemistry faculty of Belarusian State University. My master's program is nuclear and radiation safety. I graduated the university this year, Belarusian State University, specializing in high energy chemistry. My research interest is environmental radioactivity and radiological monitoring. For example, we measure average indoor radon concentrations and other measurements of natural radionuclides such as potassium 40. And this is my third time at this school on radiochemistry, and I'm extremely grateful for this opportunity to expand my knowledge on this field. And I'm looking forward to working with all of you, and I'm sure we will make a great team. Thank you very much.
Thank you. Is everybody? Oh, one missed. Yep.
So, good evening, committee members, and good evening, dear colleagues. And sorry for being late. Actually, I was doing my exams, so there a bit was little late from my university. So,
The exam?
yeah, yeah. Thank you, thank you, thank you. So yes, like My name is Sri Vignesh Punaram. I'm in fourth year medical student, and to begin upon, like, there is nothing much to explain from my education portfolio, as I have just now started my journey in education. And but apart from this, a bit more about my hobbies and its milestones. I usually write poems. So the recent milestone, like not recent, the previous milestones from my country was like I was able to publish a book and publish my poem in one of the journals, and in even in international achievements. Yes, international achievements. My poem was also published in one of Mephi's magazine. Yes, it was named like Staroski Titrat. Yes. And one of my famous lines, like, which keeps me burning all the day, all the nights, is like, when you face difficult times, know that challenges are not sent to destroy you. They're sent to promote, increase, and strengthen you from inside. On this note, thank you.
Thank you. Thank you. Now I think that everybody has presented themselves, and now
What we are up to?
нам надо выйти в English 15.
Okie-dokie. So, да мне не нужен микрофон. Okay, dear. So, finally.